We're gonna wait for a couple more minutes for the audience to join us on this Zoom.
The IAEA expert mission. We are almost done. We are so sad. Yeah, but at least we learn a lot from you guys, and we have a lot of engagement from the audience. Not only on the audience on site, but also the online people. So today, this is the fourth day of the expert mission, and today we're gonna talk about the role of the about the CT optimization, CT imaging quality metrics, and role for radiologists, medical physicists, and radiographer. So we're gonna start with the first talk with CT imaging image quality metrics by Dr. Samuel Bradley. Welcome, Sam.
Thank you. All right, so we're going to start off today. We've been talking about dose reference levels. We've been talking about radiation dose all week. And we all know very much that when you want to optimize dose, you need to understand image quality. And so we're going to spend a couple of minutes now talking about we're going to talk about CT reconstruction. We're going to talk about CT reconstruction historically and the more modern versions. And we're going to talk about how the CT reconstructions are impacting radiation dose and image quality. And then I'll end today's talk talking about various different image quality metrics that we can use to characterize image quality at your hospital. So we want to be able to we need to define image quality. And so the ability to clearly see anatomy depends on the quantity of radiation that we use. This has always been the process. Radiation detection is a statistical process. In other words, the more photons or radiation, X-rays that you use, the lower the variability or less noise you'll have in your image. So looking at this pictorially, you can see two images. I know these are radiographs and we've been talking about CT, but here's a chest X-ray on the left and a chest X-ray on the right. One is imaged using a lot more photons, so there's a lot less variability per pixel than the image on the right. And the image on the right, of course, you would probably characterize as noisy. So when we call an image noisy, basically what we're saying is there's not enough radiation photons at the detector, and that is what is leading to a lot of variability in image. Now, when it comes to CT reconstruction, we have been using a variety of different methods or algorithms over the years. So if you go all the way back to the very beginning, when CT was developed in the late 1960s and early 1970s, we actually originally used iterative reconstruction. ART was a technique that is very much like, it's short for algebraic reconstruction technique. It's very much like Sudoku, where you have a matrix of numbers and you try to get all the right numbers in the right location. The problem was, as difficult as simple as ART was, computers back in the 1970s were very limited. And so even these very simple initial iterative reconstruction techniques were too consuming for the reconstruction algorithm. So they came up with what's called filtered back projection. And we'll talk a little bit about that in the next couple of slides. And filtered back projection basically dominated for 2 to 3 decades. And that was because, as we'll show in a moment, it's fast and it's very straightforward. So it doesn't take a lot of computational power to get a good CT reconstruction. But something happened. In early 2000s, we had several papers that were published that shined a light on radiation dose. And they were both for pediatrics and adults, but really what ended up happening was we started pointing out the fact that CT radiation dose was much, much higher than, of course, other modalities, and that maybe we should be concerned with the amount of radiation. So that was the beginning of a process that led to the resurgence of iterative reconstruction. And iterative reconstruction, all the major vendors, here I'm only listing 4, Canon, GE, Siemens, and Philips, but Hitachi, United Imaging in China, all of the other CT vendors, they all have iterative reconstruction. And what happened was in those kind of that late decade in the early 2000s, we started seeing one after another innovations in the use of iterative reconstruction. And then if you fast forward to around 2019, that's when, it's about 2017, 2018, 2019, that's when AI became a big player in image reconstruction. And so we started using deep learning reconstruction techniques. Initially, the first couple of options from Algomedica and Claripy, these were algorithms that could work independent of the type of scanner you have. So if you had a Siemens, a GE, a Canon, a United Imaging, you could have these algorithms, and what would happen is you would reconstruct the image on your CT scanner, you would send it to their algorithm, that algorithm would clean up the noise and then would push it to PACS. Whereas what happened in 2019 is GE and Canon came out with their versions of deep learning, and those of course happen on the scanner and then they go straight to PACS. Other vendors such as Philips and probably Siemens at some point, they're all working on and will be soon to release their version of AI. So we've come a long ways. We started with iterative reconstruction, went to filter back projection, back to iterative reconstruction, and now we're using some really fancy AI techniques to image CT. So what does that have to do with image quality? Well, we need to talk about how we reconstruct an image in CT, and we'll find out how absolutely important the different steps in reconstruction play in the way we look at image quality. So you all know this. As a very quick review, in CT, of course, we have the X-ray tube and then the detector and the patient somewhere in between. And so when we turn it on, we get radiation through the patient onto the detector at one angle. At this one angle, we call this a projection. And of course, CT spins around the patient. So at every angle around the patient, we're collecting all of these projections, radiation passing through the patient and being detected on the detector in the back. And we collect all of these and we place them in what we call a sinogram. And so for every row in sinogram, it lists every one of the exposure events in each detector. And then, of course, as we go down the sinogram, that represents every different angle as it spins around and around the patient. So we get this, and we call it a sinogram just because, as you can, unless an object is dead center, if it was dead center, and when you spun it around and the system spin around, that would project a single line straight down. But if anything is off center in the body, it's going to be at different points as the machine spins around, and it will carve out something that looks like a sinogram. So mathematically, it looks like a sinogram, so they just decided to call it a sine. It looks like a sine function, and so they decided to call it a sinogram. So that's kind of where the name came from. But what we do is we collect all of those projections, and then once we have all those projections, we can do something called back projection. It's kind of the radon transform out mathematics, and we just back project the data across every different angle, and we're able then to reconstruct what's inside the object or the body without needing to, look into it or cut into it. So it's a very simple mathematical process to reconstruct the image. But the problem with a back projection is digital imaging is not perfect. And so if you simply do a back projection, this is what you would get, a very fuzzy, hazy image. Because every time we have an interaction on the detector, we would expect just a perfect point source interaction. The X-ray comes down, it interacts with the detector, you get one teeny interaction. But the reality is it's imperfect. Digital systems are imperfect. And so actually what will happen is you'll get a spread of signal on that detector. And we call this a point spread function. So that means every point in this object, it's not sharp, but it's a little bit blurry on the edge. And so what we needed to do in CT reconstruction worlds, we need to get rid of that blur. And because when you take that blur and then you back project that blur, it adds a little bit of signal to each of the detector elements all the way around, and you get just this hazy, hazy look. So we need to get rid of those tails, the point spread function tails. We want a single, what we call delta function, a single point on the detector that doesn't interfere with the other detector elements. To do that, we introduce what's called a filter, and that's why we call it filtered back projection. We simply take that point spread function, as you can see here, and what we're going to do is we're going to filter off the tails as best we can so that we get just a single point, a single delta function. And by doing that, what we do is we introduce negative values on the signal. And this is all purely mathematical, so you don't have to try to conceptualize what a negative number is in signal space. But what we do is we introduce these filters, and it cleans up that little spread of data. And what it does is it does two things. One, it gets rid of that image blur around an object, which in a sense, two, it sharpens the object. And so here you can see, here's a point spread function that's been convolved with a filter, and that filter gets rid of all the signal around the edges of that signal, of that object. And then as you back project it in all the different angles, you get a point. And so the edges around that are all nice and cleaned up. And so filtered back projection, first of all, mathematically is very simple and very fast, but it also is very sharp. And so we have been using filtered back projection since the late 60s, really up through the 2010s, and it was mostly because it was fast. And our radiologists became used to seeing images, reconstructed images, that had kind of a sharp, crisp boundary on all of our objects. The problem with filtered back projection is that it is limited by how much radiation is on the detector. So if you put a lot of radiation on the detector, you'll have a little bit of noise. If you put a little bit of radiation dose on the detector, you get a lot more variability, and so the image becomes noisy. And we see that, of course, in some of the most difficult areas to penetrate, such as laterally through the shoulders. Very noisy, lots of streaking. All of this is a symptom of not getting enough radiation on your detector. And if you project that signal from this lateral projection through each different angle, what ends up happening is every pixel in your image will be tainted with noise. And so filter back projection, though it's fast because you just simply back project everything in every angle, it's also limited because you take whatever noise you have in any one projection and you spread that noise through every pixel as you back project. So fast, but limited because there is a direct connection with radiation dose to noise. So fast forward back to the early 2000s when people started publishing papers and started questioning how much radiation we were using in CT, scientists immediately wanted to try to remove or try to weaken that link between radiation dose, or the amount of radiation dose, and the amount of noise in the image. So we know that iterative reconstruction can do that because iterative reconstruction, as I'll explain in a second, it doesn't necessarily assume anything. It doesn't back project. What it does is it tries to clean up the data as it iterates over and over and over again. And so with the faster computers in the late 2000s, we basically moved forward and introduced iterative reconstruction. Iterative reconstruction works wonderfully in areas that are uniform, topologically uniform. So think of a filled bladder. The inside of that bladder is largely just liquid. It's just uniform. Or if you can think of certain parts of maybe the liver, whatnot, the liver parenchyma, where there's no vasculature, it's just uniform structure. And so what happens when we do an iterative reconstruction when we use iterative reconstruction to create an image, what we're basically doing is we're looking at every pixel and we're comparing that pixel with its neighbors. And we're saying, hey, if I look at these 9 pixels, I have a certain amount of variability. I want to remove that variability by averaging all those 9 pixels and putting that value back into this single one. And then we move to the next one and we look at its neighbors and we move to the next one and the other, et cetera, et cetera, et cetera. So you can imagine this process works really well if it's nice and uniform. If we were looking in the bladder and it was all nothing but just liquid, you could probably clean up all the variability from the noise very simply. What happens though if, as you're doing this, in this row right here is the edge of the liver, or there's a bone right here. And so when the pixels start going, okay, this one looks close to this one, this one, this one, this one, this one, but whoa, the change from this pixel to this pixel, there's a significant difference. The system has some logic built into it to say, well, that's probably actually structure, not just random noise. And so what they've introduced are what are called regularization functions or penalty functions, such that when it's doing its search, looking for noise and cleaning up noise, if it ever comes to a point where there's a hard edge, there's a very distinct signal, it doesn't apply as much iterative reconstruction, and is trying to preserve the boundary effect when you reconstruct. And so it gets rid of the noise, but tries not to affect the edges of structures. The problem is it's not perfect. We know that, and just because we've been using iterative reconstruction now for a decade, we know that it's not perfect and it actually kind of softens the edges of our structures. So they've additionally added different tools, different mathematical approaches to try to penalize the algorithm from not affecting edges of a structure, such as they put in these beta functions, which will give the user the option to pick how many times it'll iterate. So if you're picking, say, maybe a factor of 1 or 2 or 3 or 4 or 20%, 30% or 40%, what you're saying is, I'm going to force the system to stop at a certain point so that the noise will maybe clean up, but the structure edges will not be as affected. It's an imperfect approach to trying to remove noise but yet preserve the edges of a structure. So filter back projection image, as you can see in the upper right hand corner, are images that our radiologists have used for decades. They got very used to the sharpness, the crispness of the edges. They, to a certain extent, got used to the noise and the noise texture. And then along came various different forms of iterative reconstruction, which is an image you see down here. Just looking at these two images, you can probably subtly see the difference. So what I've done here is I've simply subtracted these two images, and that's what you see right here. Everything, every pixel, every white or black value you see in this image right here is a piece of data that was removed from this image right here. So I hope it projects well in the room and online, but you can probably start to make out some of the borders of some structures. Liver, you can definitely see the vertebral body, maybe the kidneys over here, a little bit of the spleen, this little air pocket over here in the bowel. You can see that it's actually taking structure away from the image. And that's because of that penalty function. It struggles when you have an abrupt edge. You have uniform background in the liver or the bladder, and then all of a sudden the bladder edge. And so as much as we've tried, it struggles with that. But now if you compare little areas like right here, this red arrow, it actually works very well. You can see the amount of noise it actually removed here in this subcutaneous fat. It's generally uniform, and so this algorithm was really good at removing that. But then you look at this blue structure here, looking at the sides edge of the kidney and the spleen, it actually took part of that away. If you look a little higher up in the thorax, you can see even more. Look at all the lung parenchyma, look at the vasculature. You can pretty much read this. I mean, one would hope that some of these structures weren't even nodules, you know. Obviously, it's mostly just vasculature, but you can see how much of the information in the lungs actually gets removed when we use iterative reconstruction. All right, so iterative reconstruction, wonderful. I haven't really talked about it, but it allowed us to do a lot of wonderful things. We were able to remove dose, or reduce dose in a way. Basically what ended up happening is because iterative reconstruction uses an algorithm to take the noise away instead of using more photons or radiation to take away the noise, we kind of weakened or broke that link between using radiation to improve image quality. We now use an algorithm, we use mathematics to improve the image quality. It's not perfect, as we just demonstrated. So with technology, we now have introduced deep learning algorithms to try to improve upon the removal of noise but preserve the edges of structures. So deep learning algorithms have been inserted into the iterative process. So you're still iterating, but instead of using a regularization function to kind of go around cleaning up like a little, what are those called, Roombas that just float around all your house picking up trash, instead of trying to go around the image cleaning up the noise, now what we're doing is we're teaching the machine to recognize what is noise and what is a structure, anatomy. And so here we go. What we end up doing is they fed a lot of thousands of images of rather high dose, low noise images into an algorithm, and low dose, high noise images. Same patient, just acquired in different ways, and there's lots of different algorithms and techniques, and there's an hour-long talk we could just talk about this one step. But basically what it is the system learned that the difference between these high and low dose system noise images was largely just stochastic noise. So once it learns what the noise patterns are, you can then simply apply this algorithm to remove noise instead of needing to use that regularization function. So now what I'm showing you here is you've already seen this image. This is a subtracted image using iterative reconstruction. Filter back projection subtracted from iterative reconstruction. Now I've taken filter back projection and I've subtracted it from an AI or a deep learning algorithm. So comparing once again those areas in the subcutaneous region where it's pretty uniform, both algorithms did really good at removing noise. I would argue there's probably a little bit more noise texture in here that's been, not texture, but pixels that have been removed. And then down here, remember, we were seeing all the outlines of the various different organs. They're still sort of there, but I would argue they've improved. You can't really tell as much the spleen, the kidneys, maybe the liver, what's it called? The liver, the colon, the bowel itself is largely, you really can't tell, which means more of the structures, the edges of the phantoms are preserved using AI imaging. And if you look up in the thorax, which we knew the the iterative reconstruction algorithm really struggled with, look at that. You don't really see a lot of the lung parenchyma and the vasculature. It's mostly, it's just noise, it's just texture that you see that's moving. So AI has come a long way to to preserve the structure edges, but remove noise. So here's just a simple example. This is the same patient, was acquired, and all I did was reconstruct them using filter back projection, a form of iterative reconstruction called model-based iterative reconstruction, and a different form of iterative reconstruction called statistical-based iterative reconstruction. And you can see both of these iterative reconstruction algorithms actually reduce the amount of noise in the image, but to a certain level, it changes the way the image looks, right? The texture changes. So now with deep learning iterative reconstruction, it removes the noise very much in line with the different iterative reconstruction options, much less noisy than filter back projection, but the texture, the way the image looks, it looks a little bit more like iterative reconstruction because the edges are a little stronger, a little sharper. All right, so, whoops, what was all that conversation about? Let's talk image quality metrics. Modern CT was able to largely reduce that link between dose and noise. Today, we can remove image noise without increasing radiation dose, but we saw that iterative reconstruction, and to a lesser extent deep learning reconstruction, they change the way the image looks because there still is some edges that are removed. We need image quality metrics that can measure the nonlinear properties of noise. And so that is what we're going to talk about today. There are two ways to approach image quality analysis. One is using objective tools, such as mathematics. We can use equations to draw ROIs and make calculations, and we can measure, and we can say this image is 10% less noisy than that image, or this image is 10% sharper than that. It's objective, it's mathematical. Or we can use subjective. Subjective takes observers, maybe, such as radiologists, and we have them look at those images and we ask them to rate them and say, hey, do you like this image? Is it good? Is it bad? Can you count the same amount of lesions in this? Can you see the fractures, etc.? We ask them to do some kind of diagnostic task, and then we measure how well they do that task. And we do that across different types of images. It's subjective because the image quality metric is very dependent on observer experience, a resident versus someone that's been a radiologist for 10, 20 years, and it might even be preference related. Some radiologists prefer to see images a certain way. So let's talk about both of these. Objectively, the task of image quality metrics can be broken down to be several different things. These are things that we need to characterize to quote-unquote define image quality. First is to how we can visualize spatial detail. How close can two objects be that we can resolve them or differentiate that they're two different structures? So right here, one would argue that's probably one big blob. But one would look at these two structures and say, yeah, I would say there's two objects. So we need to define second, we need to define the sharpness of the object's edge. 3, we need to characterize how much noise is in the image. And then as we noticed with iterative reconstruction and to a lesser extent deep learning, the noise texture changed. You know, the appearance of the image looks different. So we need to be able to characterize the texture of it. And we need to do all of this for both high and low contrast physiology. We need to be able to characterize how the system works when you're looking for soft tissue masses, low contrast structures and lesions. And we also need to be able to characterize the difference in such high contrast structures such as maybe bones or anything of that nature. So what are the tools that we have typically used historically? With filter back projection, we were very comfortable using two terms or two metrics called contrast to noise ratio, CNR, and signal to noise ratio, SNR. So what you could do is you could come over here and you could take an image and you could place an ROI in the background and you'd get your typical statistics, mean, standard deviation, max, min. And then if you wanted to, I know this is a vessel, but let's just assume this was a lesion. We wanted to characterize the signal to noise ratio in that lesion. We would then draw another ROI there, and then we would get the mean, standard deviation, max, and min. So we could come over here and we could calculate signal to noise ratio of the background. So that's the mean of the background divided by the standard deviation, which is noise. 120 divided by 15, that's where I get the numbers here. So it's got a signal to noise ratio of 8. And in this case, I know that once again, I know this is a blood vessel, but let's assume it's a lesion. And so we would look at the mean of it and its standard deviation, and lo and behold, its signal to noise ratio is a little higher. So good, maybe it's a perfusing lesion, and what that means diagnostically is something different than a non-perfusing lesion. So this is good. We can characterize the signal to noise in the image. Obviously, if there was more noise, so less radiation, the denominator would get bigger, so these values would go lower. So noise directly impacted signal, obviously. It covered it up. Now we could also say, well, what's the difference between the contrast of the background to this quote-unquote lesion? Well, now we just take the difference between the means and we divide it by the noise, which is measured in the background, so the standard deviation in the background. And we do a couple quick calculations and boom, we get a contrast to noise ratio. And once again, if it becomes noisier, this value gets larger, so this number would go lower. So more noise, less contrast to noise ratio. We're very comfortable with that, right? Here's one image, filter back projection. Here's another image, iterative reconstruction. Let's go through the same, there we go. We go through the same mathematical exercise, and lo and behold, it's the same CNR when we compare the two structures. But are these two images the same? No, they're not. We look at them and you can definitely see this one looks different. And that is because what else has changed? In iterative reconstruction, the way the noise is removed changes its structure, its texture, and it also affects the edges of the boundary edges in our objects or organs. So CNR and SNR do not characterize spatial resolution or sharpness, and they do not characterize noise texture. And that is the nonlinear effect that iterative reconstruction and deep learning reconstruction have introduced into the task of image quality, objective image quality analysis. So we need to go beyond using CNR and SNR. Here we go. There we go. Sorry, I didn't mean to put those, animate those. We need different tools. So we're going to talk about the types of tools now that work. I'm back. Take a little break. I can dance for you. So we needed to talk about some mathematical metrics that can characterize these various different tasks. So such as image sharpness. The one that we use quite often in physics is called the contrast-specific modulation transfer function. It looks like MTF because it is an MTF, but it is specific to, if we measure this in a high contrast object or a low contrast object, that MTF, that modulated transfer function, will change. So that's why we call it a contrast-specific or a task-based specific MTF. So what does it say? Basically what it says is, here I got a structure. If I was to take a line profile right through the middle of this structure right here, just take, and we measure right down the middle of it, you can see there's areas of white, high signal, areas of black, low signal, high signal, low signal, and you can see very easily the distinction between this white and that white object. Definitely, there's this big, huge black space in between. So there's no problem. We can also see how sharp it is. We can see all of the structure. There's good contrast. But as we get to the point where the objects get closer and closer and closer together, and they get smaller and smaller and smaller, our ability to distinguish contrast between the two objects diminishes. And that's why this blue line drops off and just falls away. So the TTF, or the MTF, characterizes our ability to see contrast as a function of spatial resolution or frequency. And so once again, now MTF helps us determine image sharpness in contrast. Obviously, we've been talking about CNR, SNR, about image noise. They're good because CNR and SNR can measure the magnitude of the noise in the image, but we need something to measure the texture. So instead of using CNR or SNR, we now use something called noise power spectrum, or NPS. And so we go in and we place a bunch of ROIs into the signal, into a region of uniform area, and measure the amount, the variance of noise. That's what we see here on the y-axis. And now the texture, or the frequency content. Excuse me. Here you can see filter back projection and a couple of different versions of iterative reconstruction. Iterative reconstruction does great. It removed that noise variance. There's less noise in iterative reconstruction. But the thing you notice here is, if I were to pick the middle of this peak right here, a filter back projection, it does not align with the middle of iterative reconstruction. It actually shifted left. And if we applied even more iterative reconstruction, it shifted even more left. So what we found was iterative reconstruction tended to shift towards lower frequency. So what does that mean in the image? The lower the frequency, the coarser, the more blobbish, the more soft the texture edge becomes. The higher the frequency, if we go farther this way, it becomes more sandy, more textured. So noise power spectrum is great. It measures both the magnitude and the texture of the image. There's two different algorithms I really like to use when I try to characterize the noise power spectrum when I'm comparing, say, filter back projection, iterative reconstruction, and deep learning. One is called the noise magnitude ratio, NMR. The other one is called the center frequency ratio, CFR. Here's the equations, but the noise magnitude ratio basically takes, and you integrate, so you sum up all of the values underneath the curve, and we're going to do this for either IR or an iterative reconstruction, because we're going to compare it to the noise power spectrum of the filter back projection. So we sum up everything under here, and we sum up everything under the purple, we divide it, we take the square root, and we get a number. And then the CFR takes the center frequency. So like I said, it kind of finds that center point on this curve. And so we're going to take the center point of the iterative reconstruction, and we're going to divide it by the center point of the filter back projection. So it's very simple. It's actually really simple math. But what does it tell us? So in a paper that I've been working on, hopefully it'll get published one day, we looked at iterative reconstruction on our Canon scanners using ACE, which is their first generation iterative reconstruction, and our GE scanner, which uses True Fidelity, which is once again their first generation deep learning. A couple things we notice real quick. First of all, filter back projection versus iterative reconstruction. Once again, yes, iterative reconstruction is lower in noise than filter back projection. Oops, there we go. There's a certain amount of change in the peak. We'll talk about that a little bit more. You see how the peak of this yellow curve is a little different than this purple curve. And then these dash curves are the deep learning curves, the deep learning algorithms. All of the vendors come with usually 3 settings or 3 flavors: low, medium, high, low, medium, high. And so what I did is I just did all these calculations, calculated noise power spectrum for all 3 of them, and I calculated the noise magnitude ratio, just basically the area under the curves And what happens is if you see an NMR that's less than 1, that means there's greater noise reduction in hybrid IR, in IR or deep learning. And you can kind of see over here, where's my NMR? Right there. So obviously 1 for filter back projection, but all the numbers, 0.69, 0.51, 0.43, 0.28, high levels of deep learning remove a lot of noise. And then the other vendor down here, 0.72, 0.86, 0.77, 0.67, they removes it, but at a slightly different level. If the NMR ever equals 1, then there was no change. That means the noise in one image would be the same magnitude as the noise in the other image. So this is great. That's a great way to compare the magnitude of the noise. Now let's talk about the texture, or the shifting of the frequency. So using the CFR, now what we're going to do is we're going to assess the magnitude of change. If you have a CFR that's equal to 1, that means there was no shift. The texture would be the same in both images. A CFR less than 1 represents softer noise. So you can see here it's a little bit coarser, a little softer. CFR is greater than 1, the noise texture would look more sandy. So you can see the distinction between the two. So now I've gone over here with CFR for one vendor. You can see 0.93. In this case, for the IR, it softens the image. But then for the deep learning, see how it's over 1, 1.36, 1.27. High goes down below 1. For these low and medium settings, it actually sharpens the structure. It sharpens the texture in the image. And then if you go real high, then it starts to soften the image again. And down here you can see CFR 0.75, so it softens the image, then 0.93, 0.89, 0.84. It's basically close to 1. In other words, at all of these levels of AI, iterative reconstruction, the noise texture largely stays the same. So noise power spectrum is great, and then using it to analyze the overall magnitude of noise in the image and the amount of shift or change in texture. That metric's wonderful when we're characterizing image noise. So let's talk subjective. So now that those are a couple objective metrics that you should be able to use in your day-to-day tasks. Now what we're going to do is we need some guinea pigs. So we're going to reach out to our radiologists. And we're going to say, hey, radiologists, we love you. We want you to look at 300 images. And we want you to tell us if they're good, bad, ugly. Tell us if you can do what you need to do. And then they go through this exercise, and we take all of their responses, and we do some statistics called receiver operating characteristics, and we calculate them and plot them, and we get these curves. And what you see here is this dashed line going kind of from diagonally from top to bottom on this curve. If any curve ever fell on this number, that means that it's 50-50 equal probability. In other words, if you were asking the radiologist to detect an abnormal signal, so is there a lesion in this image or not, and their response fell on this dashed line, that means they had equal chance to see it or not see it. So that's not a good thing. We don't want our radiologist to have a 50-50 chance of seeing the lesion. So ideally, we want these ROC curves to be up, high, and over. In other words, what they have is a very high sensitivity of seeing the object and saying, yes, there is disease when there is disease in the image. And they have a really high specificity, which is pulling the curve this way up to the corner, which means I know that this image is normal when it's normal, i.e. there's no signal, there's no lesion, or it's abnormal when it truly is abnormal. So we can do this, and it's great. We have lots of papers out there in the radiology world where we look at these subjective reviews, we do the math, we get some scores, and we get these plots. So subjective image quality analysis has its place. It's very important because what I can do is I can take these two brains exams, I can reconstruct them differently. I can even go in and objectively make a measurement. Oh, look, there's 6 Hounsfield units of noise. Ooh, there's 3 Hounsfield units. The image on the right is definitely better, right? The image on the right will make my radiologist happy, right? Because it's got less noise. But subjectively, every time I showed my neuroradiologist this image, they didn't like that image. This one over here? Yeah. Our neuroradiologists, very much like Tanya just mentioned, they don't like this one because it softens it. The gray-white, you lose gray-white definition. You lose a lot of a signal in the image. Yeah. Yep. And that is the difference between objective versus subjective. So Subjective has its reasons. We need the eyeballs of the people that are looking at the image so that they can say, I'm confident that I will be able to do my diagnostic task. All right, so edges are too blurry. We lost a lot of information. Whoa. Hey. I put some animation in there. That's kind of fancy. I didn't even realize I did that. So, what is the limitation of subjective imaging? Well, the limitation is when I ask a radiologist to look at hundreds or even thousands of images, that's tedious. That's time consuming. It actually costs money when you do a study. You have to pay for the radiologist's time. And the reality is there's fatigue. If they have to look at 5 images, okay, 10 images, 100 images, they start to get fatigued. And there's all that subjective preferential treatment of different looks of an image. So can we do something mathematically that mimics the way a radiologist looks at an image but doesn't use a radiologist? And so that enters this beautiful equation. We love math, don't we? Equations are beautiful. And if you notice though, look at this equation. There's some things in here we recognize. TTF, noise power spectrum. So some of the metrics that we've introduced today and we've been using now for now over a decade or more to characterize image quality, they're part of this equation. So what is this? Let's talk a little bit about it. So what this does is it's combining the TTF, the noise power spectrum, and what it's doing is it's going to compare the image quality metrics and it's going to test the system as we look at a task. So what if we were to introduce different size lesions with different, structure? Is it low contrast, blurry around the edges, high contrast? We don't have to do spherical. We can do lobulated, spiculated. We can do any kind of lesion. It doesn't even have to be a lesion, but we need to introduce some kind of test. We're going to check to see that this image and this algorithm how well it can be used for diagnosis based on whatever we use. So we're going to do a couple of different tasks. And the beautiful thing about this is this algorithm right here called D prime, we can go in because it's mathematical and we can acquire lots and lots of images at different doses, different KV values, different MA, different phantom size, all of this. We can check all of these different different acquisition techniques. So we have thousands and thousands of permutations of how this image could look. And because it's mathematical, a computer can crunch through this in seconds. If I asked Tanya to look at 100 images at different doses, 100 images at different KV, 100, et cetera, she'd smack me. It would be very, very difficult to do that. So the beauty of using math is that it's something that can be used to look at all different variations, and it can be used in a very timely manner. So in a paper that we published a couple of years ago, we applied this algorithm when we wanted to ask ourselves, which algorithm is going to give us the best diagnostic confidence for our radiologist? Filter back rejection, one version of iterative reconstruction, another version of iterative reconstruction, and then, of course, our new deep learning reconstruction algorithms. And the way we did this is we took all of our TTF measurements of the image, we went inside our patients and measured the noise power spectrum inside. We were specifically looking at the liver background versus lesions. And we got all of this data and we put it into that algorithm. And what we came out with, and I'm not going to go through the details, it's really not that important for today, is you can see up here the iterative reconstruction curve is higher than the different the deep learning curve is higher than the different iterative reconstruction curves and definitely higher than the filter back projection. And it's really, really good, gives us higher diagnostic confidence, better ability to see smaller objects. And we actually tested this for different contrast levels, subtle contrast differences of say 50 Hounsfield unit all the way up to 300 Hounsfield units. The beautiful thing is you can see no matter if an object gets larger and larger, and I think our radiologists would agree, if you have a very big fat lesion, it doesn't matter how noisy the image is, you can probably see that lesion. But at the very subtle level, at the very low level where you have two teeny little structures, how well can you see that? So this is mathematical, right? For me as a physicist, this is beautiful. I love this. This tells me exactly what I need to do to change the technique factors in my image. What does that relate? How does that relate to real world example? So in another paper we published, we looked at iterative reconstruction versus deep learning reconstruction. And we did it for a very simple task. We asked our radiologist to look at and count how many stones were in the image. So this is a very easy task in general. I don't think our radiologists worry too much about this. And so here you can see iterative reconstruction. You can see here in the left kidney, you got a stone, right? Hopefully you guys can see that. Down here though, in AI, wait a minute. And when the radiologists looked at this, they were blinded. They only saw one image at a time. So they would count this separately and they would count this one separately. And so in this case, they counted 2 stones. And what ended up happening is we had to ask ourselves, well, is this a fluke? Did the AI introduce false signal, introducing an actual stone? Because we only counted 1 in IR. And if you come over here and look at the coronal, of course, you can actually see that, yes, there were 2 stones the whole time. And so what this demonstrates is the AI algorithm gave us higher diagnostic confidence when we were looking for smaller objects. And so we can use that D prime algorithm to predict the response, and so we can set our noise or our dose targets, and we can pick the different levels of iterative reconstruction or the different levels of deep learning, and we know basically what that means once it is used clinically. So that's just a classic example of that. All right, for all of you that just love doing this, love the math, it might feel somewhat scary because those are big equations, right? Those are not so simple to use. Well, luckily for you, there was a paper, we wrote this several years ago. It's a task group from the AAPM. It's free for all members of the AAPM, physicists. And you can download it, and it gives you just all the detail of how to calculate a TTF, how to calculate a noise power spectrum, how to use D prime. It goes into all the detail that you could ever want. And there are some softwares, actually a software that you can download for free. It's right here. Just go to this website. And you can have the ability to now do TTF, MTF, TTF, I should have put TTF there, NPS, and D prime. You can do all these calculations now on your own. So this is a free resource for you. And the basic point here, what I'm trying to say is we need to move away from just using CNR and SNR when we deal with iterative reconstruction and deep learning, which is the future and the present of CT reconstruction. All right, so in conclusion, collecting and analyzing dose is important, but radiation dose without the context of how good the image looks, or quote unquote, an analysis of the image quality, is only 1/2 of the picture. If you just simply lower your dose because it's lower than the DRL, you're actually doing a disservice for our radiologists, and more specifically, we're doing a disservice for our patients because we potentially are missing findings in the image. There are multiple ways to review image quality. We went through all of those today, but modern reconstruction algorithms, especially using AI and deep learning, they require the use of more complex, nonlinear image quality metrics. So with that, I will thank you.
Thank you so much for the lectures and a lot of formulas, number
They're the
for
best.
me to learn. Yeah, very interesting. So as an end user, as a radiologist, those reconstruction technique, can I choose, or like are you guys going to be the one who decide for us? Okay.
So definitely, yes. A choice should always be made, and we talked about this through the paradigm or the lens of dose reference levels. But a dose committee, someone that makes these decisions, should always incorporate a radiologist, a physicist, a technologist, and sometimes a PAC specialist or an IT specialist for all the other things. But the reality is, I as a physicist can go in and I can do all these fancy calculations and I can come up with what I think is the best looking image. For example, that brain image on the right-hand side, I was actually pretty excited. I'm like, oh, my radiologist is going to like this. It's lower noise. And she took one look at it and says, no, I don't like that. And so that's the beautiful thing. We need our radiologists because they're the ones that actually use the image. And then we need our technologists because they're the ones that will actually obviously scan our patients and they do all the processing. And most of the time, the radiologists, when they have a question, call the technologist and say, hey, can you do a different reformat? Can you change this? Can you change that? So the reality is, though, is we as a team, radiologists, technologists, physicists, when we get new technology, when we get new CT reconstruction algorithms, what we need to do is sit down and we need to decide how strong, what level we're going to implement, what our dose levels are going to be, And once we figured all that out, it's turned on. And now it runs hopefully seamlessly in the background.
So which means normally this reconstruction technology come with like a package from the vendor,
Yep.
right? Like, okay, this is a package that we can offer you. You can see this thing better on this model and maybe that thing on this model.
So the deep learning algorithms definitely are going to be found on your more modern scanners. So for example, we have the ACE that I've demonstrated from Canon. I know for certain you can get that on their Genesis and Aquilion line. I'm not certain about the Prime line. I don't know. Definitely reach out to your Canon representative. They would let you know. Same thing with GE. I know initially it's only on the upper level Revolution Apex, but Canon and GE, and as Philips and Siemens will eventually do, they're always usually pretty good about backwards compatibility. They introduce it on their top line. They want you to go buy a new scanner, but eventually they find a way to get the AI and especially the IR algorithms down to even the older systems. So if it's not there yet, for example, for those of you that have GE scanners, I'm sure you could eventually get true fidelity. If you don't have a Revolution or an Apex, I'm sure you could eventually get it on your Optimus and whatnot, your older generation scanners.
I think at the end you still need me as a radiologist for the subjective test. You cannot use just like a mathematic because I am an end user. At least you need like to use me, maybe like a small sample and use that thing to extrapolate for the calculation or something. You cannot get rid of me.
Yeah, that's a great point.
Right.
And
I just wanted to point out exactly like what Sam said. When we have GE, when we wanted to implement AI, what we did is there is low, medium, high. So we would do our regular scanning, but then we would tag on 3 more reformats with those, and then the radiologists would look at it. And so we did that for many cases until they told us, okay, you know what, we definitely want low or medium. The high, as Sam showed, has some problems with high. You know, it looks too soft, looks more a little bit artificial almost. So the low or the medium is typically what they go with. But you have to go back and forth, and all 3 are involved. The physicist is involved just if there's a dose question and talking about the way Sam discussed, and the radiologist, totally you're relying on radiologists. Because as Sam said, you know, we might like the image with the lower noise, but you're the one who's reading it and says, no, I do want a little bit of noise in the image. So you guys are really setting up my next 3 talks because it's important to have that collaboration between the 3 professions, radiologists, technologists, and physicists.
Yeah.
Not anyone. Math is not going to solve the problem because we are not the ones reading.
no, don't listen to her. Math solves all problems. No, but I completely agree with Kalpana. I would tell you the way I use my D prime is because when you sit down and you have the task in front of you, I have new reconstruction algorithm. I have true fidelity, I have ACE, I have whatever, even different iterative reconstructions. The question is, okay, well, what mass, what KV, what dose level, what reconstruction out kernels and filters should I use? And all of a sudden you have this multi-level matrix of options. And if you do submit all those images to the radiologist, it will become difficult. And so what I like to do is use those algorithms to weed it down. And I can quickly go in and say, okay, if I change this KV and this MA and this filter, oh, there's my curve. And then I do this, oh, that curve wasn't as good. And so I can immediately say, okay, I'm going to weed out 80% of my crazy ideas, and I'm going to come down to, say, 5 or 6 good ideas. And just like Kalpana says, I'm going to then present those to the radiologist. We did the exact same thing she did. We simply did our standard of care for us, which was iterative reconstruction and all of its reformats, sagittal formats and coronals and all that. But then we appended on the back end of that in packs for probably a good part of 6 months, probably a little longer than that, our DLRs, our deep learning algorithms. And they got to the point where they would open up packs and they would quickly go straight to the AI, and then they would just ignore the IR version. And we said, okay, fine, well, we're just not even going to send those to you anymore. And so absolutely, radiologists aren't going to go away, but they just have to be friendly to the physicists now.
That's true. Any questions, comments, Sapapong?
This is going to be something new to us, the way we train our radiologists and the technologists, because in the old days, like even now when I do lecture the radiologists, we are based on like common, like simple image quality metrics like CNR, SNR, and they understand. But to move to like deep prime or other quality metrics, then we may have to discuss and see what can we do so that they understand the contribution of how the medical physicists can do in clinical setting. And also we should somehow educate the technologists also, because we work together within the team. So it should be a good start to implement this kind of quality metrics in clinical practice. Yeah, we do. Yeah.
They don't use it?
They do, but simply they just show the radiologists, and radiologists say it's okay or not okay, which like the degree of level. We do the same thing like you, just that we did not really do the image quality metrics. Just first, yeah. We need a good clinical physicist in the setting.
Yeah, it's also helpful because at the early days of iterative reconstruction, we struggled to figure out why the images looked blurry and soft, because everyone just assumed it was going to take the noise out and make everything beautiful. And then obviously we figured that out with all the math. And now iterative deep learning is on board, and everyone's like, okay, well, we're more comfortable with NPS and TTF, and we can do those calculations, and we can see now the magnitude of change, and so we can kind of quickly rule out the strongs. But we have new techniques. The second generation of AI is actually starting to come out. Canon came out with their peak this year, and now not only does it remove noise, it actually enhances object sharpness. So the question is, to what extent do we use that? So I completely agree with what you're saying, and it's always easy just to show it to them. They say, I like it, I don't like it, and go forward. But I think we can do more when we actually go in and characterize the image based on TTF, NPS, etc. And then we can go in and we can tell the radiologist why things have changed and why things are different. And then we can say, but if we use this setting and this setting and this setting, we can make it look the way you want. And so almost always radiologists are going to ask for more, right? Radiologists always want a little bit more, and so we can help them say, well, this algorithm cannot do that based on the physics of it, or this algorithm could do that if we add this feature or that feature. So they're definitely tools, and with the way we use those tools will very much be dependent on the clinical environment in which you work.
Sure. Thank you so much, Sam. So next speaker, co-partner, you're going to talk about like each role, like a radiologist, technologist, and physicist role for the CT optimization.
Okay, that was an absolutely fantastic talk, Dr. Brady. I learned a lot. I'm going to have to download that software from 233 because I haven't. So that was great. And also what was great about that talk was showing what Dr. Brady showed is how important it is to involve the radiologist, the physicist, and the technologist, because even though he did all this work, he had to still go tell the technologist to reformat those images using AI, and then we had to rely on someone like Tanya, a radiologist, to tell us how good the image is. So we're going to, great segue into what I want to talk about. The next 3 talks, you're going to see a lot of me today, I apologize, is the role of the radiologist, the role of the physicist, and the role of the technologist. And this was a fantastic example of how they work together. But we are going to change topics a little bit, and what Sam was talking about is how do you introduce new technology in clinical practice? And what I'm going to talk about, how do you maintain image quality and dose in clinical practice on an ongoing basis, not just when you get new technology. So the first talk is on role of radiologists, and then we'll talk about the others after the break. So the first thing we are talking about really is CT protocol optimization, and protocols is really the key here because everything that Sam talked about comes under protocols, right? Whatever parameters you're putting in protocols is what he was talking about. So what is a protocol? What do I mean when I say CT protocol? Well, it's a collection of settings and parameters that fully describe a CT examination. Protocols may be simple, non-con head, one maybe a 5mm reformat, and that's it. Or it might be a 3 or 4 phase liver, which requires sagittal cuts, coronal all kinds of reformatting you have to do at the back end. So it could be a very simple protocol, a very complex protocol for full-featured general-purpose CT systems. Now, if you're a hospital in rural area that does 10 patients in a week, you are not going to need a lot of complex protocols because you're probably just using it for very simple things. But if you're like our hospital or Sam's hospital, you're in a big academic center in a city where you're doing 200 patients a day, then you have all the full range of simple all the way to complex protocols. So, as I think we have learned throughout the week, it's extremely important, and very good example yesterday where we saw that one site, the dose was so much higher than the other 8 sites for head, right? There was non-uniformity, and we caught that looking at your data, right? And that happens to all of us. So it's incredibly important that protocols are uniform across hospitals under the same umbrella. So CT protocol tailored to clinical indication and patient body characteristics. If not, then the resulting image would not be optimal for indication. So, for pediatric patients, I want a certain protocol. For my adult patients, I want a certain protocol. For obese patients, anyone maybe greater than 200 pounds, maybe I need a different protocol. But I need to make sure I'm tailoring my protocol according to patient size, and then I'm making sure it's the same across all my scanners and across all my hospitals. Protocols are prepared not for each individual patient, but for a group of patients with the same body characteristics and clinical indications. So just because I'm getting scanned versus Sam getting scanned, there's a big difference in the way we look, right? He's a lot taller, I'm a lot shorter, I'm a little chubbier. The protocol for me might be different for him, but that protocol doesn't apply to Kalpana only, it applies to anybody with my body type. And similarly for Sam, anyone who is tall, that protocol will apply to them. So it's not really tailored to a patient A, but it's tailored to the body characteristics and clinical indication for that type of patient. How do we accomplish this? I mean, this looks really complex, right? We are all very different looking people, different characteristics, million clinical indications. How do we accomplish this? That's why it's incredibly important to review and manage CT protocols. You cannot buy a scanner, set up a protocol, and forget about it. You have to make sure that what you're using to scan a patient is giving you what you need. At the same time, balancing image quality that Sam talked about, incorporating new features, as well as radiation dose. So review and management of CT protocol ensures that exams being performed achieve the desired diagnostic image quality at the lowest radiation dose possible. And actually I would like to scratch the word lowest and replace it with optimized radiation dose. We are not trying to go low, which is what Dr. Brady likes to do at his hospital, but we want to be optimized dose. What is the best dose for this task? Doesn't mean it has to be the lowest dose, while properly exploiting the capabilities of the equipment being used. So that is incredibly important. If you replace your 16-slice scanner with a 256-slice scanner and you use the same protocols, why did you buy the new scanner with all those bells and whistles? So you need to make sure that when you're replacing your old scanner with a new scanner, you take into account all the bells and whistles that that scanner has to reduce dose. So for example, if I have AI on my new scanner, I need to use it because it's going to help the radiologist, right? So you need to exploit those capabilities, and that's why it's very critical to review and manage your CT protocols. They're essential activities in ensuring patient safety and acceptable image quality. It's explicitly defined as essential by several states in the United States. We have a lot of regulations in each state, as well as accreditation bodies, such as the American College of Radiology Accreditation Program, the Joint Commission, and all of them very explicitly state in the regulations that we have to do review of CT programs. For accreditation, it's about 6 protocols that we have to look at every year, at a minimum, the required, and then Joint Commission also looks at the similar 6 protocols, but as a facility, I'm not just going to look at my 6 protocols. I look at each and every protocol at my facility that's being used, okay? So incredibly important from even regulation point of view. And the reason they've started doing this, and it's probably been around now for the last maybe 10, 15 years, is because exactly that you do not want to set up a protocol, forget all about it, because it's changing with the needs of the patient population and the needs of the radiologist. So you need to review and manage it on an annual basis, to make sure you're giving the right amount of dose to the patient. So as shown here, this is from Dr. Reiser. She's one of medical physicists, and she presented this at AAPM. This is a Joint Commission requirement. Diagnostic CT imaging protocols are reviewed and kept current with input from the interpreting radiologists, medical physicists, and lead imaging technologists to make certain that they adhere to current standards of practice and account for changes in CT imaging equipment. The point I'm trying to make here is this responsibility is just not mine, or a radiologist, or a technologist. It is collectively all our responsibility to make sure what we are using to scan our patients is reviewed on an annual basis and changes made according to clinical practice. So you need a management team for the CT protocol review. No image optimization process can be carried out without assessment of clinical image quality and corresponding dose. And Sam did an incredible job showing that, right? He can't just set it up doing math. He needs the radiologist to tell him that what he did on his computer was appropriate or not, right? So you need that team to do that. So the radiologist, in my opinion, as well as the reference I looked at, is a clinical expert. They're the one who defines the imaging task, and they're the ones who will tell me, I don't care, Kalpana, what your computer tells you. I like image B versus image A, right? They are the boss. That's what they do. The physicist, which is Sam and me and Napapong here, and others in the audience, we are the technical experts, and we can suggest scan parameters as techniques, just like Sam said. He can run that computer program and say, this setting gives me the quality, at least in math, from a math perspective, that gives me good image quality. So we, the technical experts, will help with suggesting, like we did yesterday, let's drop the mass, increase the collimation beam width to drop our dose, right? And the technologist, very important as well, because they're the one who implement it. And they're the one who will come and say, well, yeah, you're telling me to do this, but here is a workflow concern that you didn't think about. They are the workflow experts, and they can provide insight into the practical limitations of proposal protocol changes. For example, when we started doing dual energy, which is a new technique with scanners, you cannot do it on GE for anyone who is greater than maybe 220 pounds because of the way the image quality looks and the limitations of the scanner itself. But it's really the tech who can tell you that more, because they are the ones scanning the patients. You might know it from a theory perspective, but really they're the ones who are seeing the limitation because they're hands-on there. I'm not hands-on, nor is really the radiologist, because they're in the reading room. So really the technologist plays also a very key role in this management system. Each individual provides a unique perspective and should be considered a long-term member of the core team. I cannot do my job as a physicist without my radiologist and without my technologist. And I don't think the radiologist can do a job without input from the tech and the physics team. And the technologist, they have all the knowledge about running the scanner, but they don't necessarily understand all the nuances of physics technical features. Plus, they're not the ones reading the images. So they need the radiologist and the physicist as well. So each of us brings a unique perspective to protocol management. So it's incredibly important that we are all there at the table when we're reviewing protocols. And actually in the United States, the state regulations, Joint Commission, American College of Radiology accreditation program, they all say when you're doing protocol review, you've got to have the radiologist, you've got to have the physicist, you have to have the technologist, which can be a real problem because radiologists are busy reading. They may not be interested in sitting down and reviewing protocols, right? So that could be a problem, but you cannot go ahead with reviewing without their input into what you're talking about. So as I said, they all require to be present as part of the CT protocol review process. Radiologists are very busy people. They may not be on site. A lot of them do teleradiology, or they're not interested in protocol. They just care about looking at the images and making their diagnosis. They don't want to know what KV and what to do with noise and what to do with dose and stuff like that. Technologists, on the other hand, are rarely given administration time to edit protocols outside of vendor training. Unless the lead technologist has half a day or 1 day to focus on administrative tasks, they don't want to be involved in this too. Physicists, even though we have no time, we are just expected, because we are the technical experts, to perform protocol review during the limited time available we have during annual quality control that we do on a CT scanner. Or we do it using, protocol dump from the scanner and do it on our own. Again, all of us are busy people, and we need to figure out how we can do this in an efficient manner. There are too many clinical, technical, and logistical facets of CT protocols for one professional to appreciate. So something that I think makes sense, as Sam said, yeah, it's a no-brainer. The image with the standard deviation of 3, which has less noise, heck yeah, that's a better image. And the radiologist is saying, no way, that's not what I like, right? So each of us needs to be there to understand what's a good image. The roles of all of us and the entire protocol review and improvement effort must be supported by administration, and sufficient time and resources must be allotted. So this is regulation, but if you don't give me time to do this, then it's not going to happen. We are all human beings. We have very busy people. How are we going to do this? So the administration, the department, has to give you time, especially the technologist who's scanning all day, to come out, and the radiologist who's in the reading room all day, to come and work with the physicist to do this. So this just is a really nice, and I forgot, see, I was supposed to put the reference and I forgot to put it. Insert Tim's book reference. It's a reference, the picture is from a book from a physicist we know in University of Wisconsin, who's written a whole book on CT. And this is a really wonderful picture that shows you need that uniformity in workflow across the different protocols, across the different vendors, and across the different experts. So protocol review and management requires a team effort. The team must consist of a lead CT radiologist, a lead CT technologist, and a qualified medical physicist. What do I mean by a qualified medical physicist? AAPM, which is our professional organization, has specific wording on who is a qualified medical. You have to have your education, but you also have to be board certified by the American Board of Radiology or the American Board of Medical Physics to be called a qualified medical physicist. So you have to have the training, but you also have to be board certified. That does not mean that if you're not a QMP, you don't have the knowledge, but this is the way it's defined by AAPM. So the team must be responsible for protocol design and review of settings, right? Each team member brings, as I said, unique perspective. And to be successful, it is important that the expectations of the roles and responsibility of each member are clearly described. So if I tell Tanya to come and do a review with me, let's look at protocols, but I don't tell her what is her role, then she is confused. She doesn't know when to speak up and to not. If I don't tell the technologist what their role is, it's like, okay, am I supposed to do this? I thought the physicist was supposed to do that. So all our roles and expectations have to be defined. And during the review process, focus should be placed on image quality, very important, but not without thinking about dose, patient care and safety, and workflow. How is this going to work for the technologist to implement the new workflow? So now let's talk with that background a little bit of the role of the radiologist, and a lot of what I'm going to talk about is what we do at our site in Seattle. So you have to assign a lead CT radiologist or a director of CT to be involved in in protocol review. They're responsible for coordinating efforts between all aspects of the CT protocol optimization team. It may be an administrator or other personnel who may take on this role. Honestly, for us, radiologists only there when we invite them to the meeting. They are not taking care of any of the administrative stuff. Actually, at my site, I take care of everything in terms of setting the meeting up, inviting the radiologists, and doing all that. They will not do that because they don't have time. So it really needs someone administrative, or the physicist can take the lead on that. They are responsible for prioritizing the efforts of the entire protocol optimization team. Again, because of the radiologist's clinical responsibilities and how busy they are, a lot of this is really done by me, where I will set up everything, they just have to show up and then give their input on the protocol. Other radiologists, very, very important, must accept the results of the CT protocol's team effort. So if Tanya is at our meeting, but she's got 20 other people in her section, if you're an abdominal radiologist, whatever changes that she agrees to or tells us to do, she needs to make sure the other 19 radiologists in her section are okay with it. Can you imagine if she comes to the protocol and says, yeah, let's do this, and then we start getting emails from the other 19, what the heck did you do, right? So there's got to be buy-in from her team when she comes. So the leader who comes to the protocol review should have the authority to make changes or implement changes, but it has to be done with cooperation from other people. And this is something in the past we have had problems with, and it makes life difficult for the tech and for the physicists if the radiologists are not in sync with each other. And trust me, that happens. I'm sure you would agree with that. So what are the responsibilities of the lead radiologist? Well, first they have to convene a team that includes a supervising radiologist, the physicist, and tech to design and review all new or modified CT protocol settings to ensure both image quality and radiation dose are appropriate. What are the benefits of reviewing protocols on a regular basis? Well, you want to eliminate protocols not used. We have tons of protocols. When you said you were starting with 14 for your DRL, I was jumping in joy. I wish I only had 14 protocols, right? We have more than 200 protocols in our, and the differences between protocol might be very, very little. So one goal that I have, which I tell the radiologists, eliminate protocols not being used. If you haven't used it in the last year, let's get rid of it. Reviewing protocols known to give high dose to ensure protocol optimization. So we have high dose protocols like brain perfusion or maybe a 3-phase or 4-phase liver or a CTA. You want to make sure those doses are reasonable. Adding new protocols. Now we got these new type of patients. We want to do this new procedure. We need a new protocol. So when dual energy was introduced for gout imaging or anything that dual energy is good at, now we are saying, okay, let's not scan this indication with regular. We want to do it with dual energy. Well, there's new indication, new way of scanning. You need to be able to have a protocol review meeting to add that new protocol. Modify protocol based on feedback. So we have a protocol and 15 of her section colleagues say, no, this is really noisy, or no, I really need a sagittal reformat on this protocol. We need that feedback to make the changes and to ensure consistent protocols across the sites, if that's possible, depending on the site and the population. So each section CT lead radiologist is responsible for reviewing the quality of the imaging studies within her section. So at our institution, I have my protocol review set up for my whole year. I'll show you my schedule in a minute. I have neuro, body, MSK, chest, cardiac, that's coming up next week for me. Trauma, because I have a level 1 trauma center, as well as other hospitals if they get trauma patient. Pediatrics, even though we don't do a lot of pediatrics, we scan anyone below 18 as peds, right? So we need to make sure we have pediatric protocol. We meet once a month, and we don't forget that you also have nuclear medicine scanners. So even though I don't cover nuclear medicine at my hospital, I need to cover the CT part of the PET CT scanner. So you have to think about those scanners as well. What is the responsibility of the radiologist? Basically, they need to be confident when they come in. They can say, yeah, I like the image quality. Let's not touch this protocol, or I hate the image quality. We need to do something. But they also need to be aware that there's a radiation dose connection with that. So they need to come and work with us and figure out, yeah, we want to increase the dose, but how much dose can we increase? Then you have to figure out the series, non-contrast, contrast, arterial phase, venous phase. Well, you're using dual energy. Do you need a non-contrast? You can have your virtual non-contrast, right? So now let's eliminate non-contrast. Things like that, you will make changes. How much contrast you want to use? So recently, what was it, a month ago in the United States, I don't know if it was the rest of the world, but United States, we had a severe shortage of contrast. And everyone had to adapt how much contrast to use, just enough to get image quality, because we were so short on contrast because the company in China shut down because of COVID. And GE provides us all that contrast that comes from China, the factory over there. That was a real learning. Everyone in 24 hours had to figure out how much contrast to use and still do patient care with that shortage. And then reformats desired. If you're not ever going to look at the sagittal reformat, let's get rid of it. So that's why these are all the things that the radiologist contributes to when we're doing protocol review. They're also responsible for distilling the wishes of their section and communicating those with the CT protocol optimization team. So even though maybe Tanya doesn't have a specific request, maybe her colleague does, and she needs to consider that and bring it to the protocol review section to implement it. They must settle on any disagreements on alternate scanning techniques to ensure uniformity of protocols within the section. And that is a radiologist's responsibility. And that is really frustrating for me as a physicist sometimes, because if the section is large and half the people don't care about protocol review, once we have made the change, they all speak up. Oh, what did you change? Everything is, well, you need to talk to the person then. We tell them, go talk to your lead section radiologist and ask them why we made the change. We are not going to do that. They need to figure that out. So it's very important there's uniformity within a section between the radiologists as well as across hospitals. In our case, most of our radiologists go between the hospitals, but some of them don't. And so it's, again, very important that all radiologists are on the same page where protocols are concerned. So this is my setup, my hospital system right here. UW Medicine, University of Washington Medicine, and these are all my hospitals. And these are some of my clinics, 1, 2, 3, 4. This is an outpatient cancer center, 5 Valley Medical Center, and UW neighborhood clinics. So you just go to a clinic in the neighborhood. That's what these are, and there are about 15, 20 of these. Luckily for me, I don't have to cover them. I cover all of this. My team and I have to cover this. We don't cover these two, but I'm pretty sure they're going to tap us to start covering them pretty shortly. But now look at this, just without going into details. How many sites do I have? 1, 2, 3, 4, 5, 6, 7, 8. And I have a mix of CT scanners, GE scanners, and Siemens scanners. Luckily, I don't have Canon or anyone else, Philips or anybody else right now, okay? So you can imagine how complicated the task already is just looking at this diagram and understanding how the heck am I going to have consistent protocol review. We put all our protocols online. This is for University of Washington. It shows us, this is our HD protocols, our old CT scanners. I just wanted to kind of show you that anyone can go online. This is intranet, so not someone from outside the university can go in, but anyone inside. And you can look at right here is, CT protocols, and you can see our MR protocols. So if radiologist wants to go from Harborview, they can go and look, or from UW, they can go and look at it. Harborview also, our trauma hospital has their own protocols as well because they have Siemens scanners. This is all GE. So we have it online as separate, but we try to keep things consistent between what we are doing on the 2 different models of scanners. And this just shows you a lot more. It shows you post-processing sheets, protocols, protocoling guide, and things like that we have online. This is an example of what our protocol sheet might look like when we are reviewing. So the way I do it, I actually administer protocol review at our sites. And what I do is I have the date set up. We project a protocol, and we don't do just the 6 that's required by regular. We do all of our protocols. We just throw it up, pull up the sheet, throw it up, and just go through it really fast. But what I tell the radiologists is not to focus on dose and image quality, because that's what my job is. They need to focus on telling me, is the amount of contrast we are using look okay? Do you want to change anything with contrast? Do you want to change anything with the anatomy covered? Do you want to change anything with the reformats with you? See right here, you can see we are using AI medium. Sam had talked about low, medium, high. For GE, we are using medium. And the docs are reading at 2.5. So we are acquiring a thin, and they read at 2.5. That's the kind of thing that the radiologist has to focus on. Do I need this reform? I don't look at it. Or you know what? I think I need coronal, or I need something else, or I don't need this, something like that. All of this is our protocol. We put it all on, we project it, and we all sit in a room just like we are sitting here, and we go through it really fast, actually, because we have a lot of them. But we do this by sections. That's why I said I have protocol review throughout the year. Again, showing you some more ideas, scan type, MPRs, superior extent, inferior extent. All of these are very nicely, this is our dual energy protocol, and so it's specified at the top what kind of protocol this is. But the role of the radiologist is really to focus on all of that. When I talk about the role of the physicists and technologists, we look at other aspects of this protocol sheet. So in summary, protocol review and optimization team includes radiologists, tech, and physicists. And now, how do you get a radiologist to come in and do this? What I do is I go to every section chief. So for neuro, I go to the radiologist chief over there, MSK chief. I tell them, please assign a radiologist from your section for protocol review. And then every time I set up my meeting, I make sure that that chief or whoever's assigned is available. But we open protocol review to the whole section. If everyone wants to attend, they're welcome to, but we need to make sure at least the chief radiologist who's assigned is available to come to protocol review. As I said, in the United States, this is a requirement. I mean, if we don't do this, we are in trouble, right? So physician, radiologist, physicist, tech, all have to take part in CT protocol review. It's typically the lead from each section or the director of CT who oversees all the section. They could be there. But again, the director of CT could be a body radiologist. They don't know what the neuroradiologists want. They might know a little bit. So we really prefer that we get this specialty-specific radiologists at the protocol review meeting. And they're really their job. Honestly, like anything else in radiology, the radiologist is in charge of things. But it's not the radiologist who deals with the details. It's the physicist and the technologist. You know, a great example of that is mammography in the United States. It's so regulated. The radiologist in charge of everything, but it's really the physicists and the tech who do all the work, right? The quality control, but they are in charge of it. Similarly, for protocol review, they are in charge of it, but we kind of take care of all the logistics and making sure things happen. They also are responsible for coordinating efforts between all aspects of the team. Section lead radiologists also responsible for making sure the wishes of their team members are taken into account. And they must settle disagreements prior to protocol review. Now, if Tanya is my radiologist in my protocol review meeting, but she only reads at one site and not at the other site, then it would be nice to have some representation of a radiologist from my other site, like 1101, site 1101 yesterday, right? You want that radiologist to be there and a radiologist because they may say, hey, our doses are high because we do blah, 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 which is different from the other 8 hospitals in Thailand. So you need to make sure, depending on your practice, that you're getting representation from all the different sites. And when we talk about the physics and technologists, I'll tell you how we get that from all sites to be there at our protocol review meeting. So that's all I had to say. Hopefully that was good. And if you have any questions, I'm happy to answer it.
That is very nice. I believe that Napapong has some questions or comments. But before we go to Napapong, you said that you do the protocol review once a month. It's like each section once a month. Seriously?
No,
Oh,
no,
okay.
no. So for the way we did it is, so before this, this has been a lot of tears and pain and sweat on my part to make this way. What used to happen was, I used to get very irritated. I used to try and schedule a meeting and everyone's like, okay, we're not available. So I finally went to the section chief and I said, look, we gotta dedicate a time every month because body protocols, there are so many different types, right? There's GU, there's GI, there is oncology, there's whatever. So for body imaging, we just schedule 12 to 1, first Tuesday of the month. We're going to look at it. We don't use all the 12 months for body. We might finish all the body in 4 or 5 months. And then you do the same for neuro, you do the same for MSK, and so that's the way it is. So we pretty much do protocol review throughout the year, but not of the same section throughout the year, different sections throughout the year.
Which means like maybe once a year for each section.
Correct.
Right? Okay.
Once a year, yes. Very good point. It's once a year for each section. That's the requirement. And with the number of protocols we have to do it more than once a year, this is formal review. If you look at it, you're continually reviewing protocol throughout the year because you make changes and things like that. But formal review is only once a year that is required by regulation.
That's what we do at Indiana University. It's maybe like they set up the meeting monthly, but it's just like a for neuro, for peds or something. It's just
Exactly.
like maybe like every 6 months or like once a year.
Correct.
Okay, Napapong, your turn.
Well, it's great talk, and I wish that a lot of people in Thailand learn about this, like teamwork among radiologists, physicists, and technologists. What we need to catch up now and in the near future is that it's like we have a missing link. We have good radiologists, we have good technologists, but we don't really have clinical physicists working in place. So probably maybe Tanya will look at the new project with the agency or something to really focus on the need of the clinical physics. Of course, we do the clinical physics training, like we have residency program for physics 2 years, but it's mainly a focus on like machine testing, quality assurance, but not really people who work in a clinical setting like this. So the US has a very good model because the way physicists train, like they have American Board of Radiology like the radiologists. So the way they work together, it more like giving the answer to what radiologists need, because the way they train it pretty much like to serve the need, and of course to serve the need of the patients too. So I think, in my opinion, like we seriously need to take this into consideration the way we go forward with the
Absolutely.
training in this country.
And also, I think not only the training, but you need to show, the country needs to show that physicists are important. And that means regulation bodies in this country and people who make decisions, authoritative bodies, they need to say that physicists needs to be involved. Only when they say that and it's a regulation and it's required, will then the things, oh, okay, like in America, right? We decided a few years ago that now every medical physicist that comes out of training needs a residency in order to be eligible to take the American Board of Radiology exam. Now, when my training, I completed my PhD in 96. I did a residency at Mayo Clinic from 96 to when it was not required. Not required. But now, you cannot be board certified until, just like the radiologist. So the medical physicist profession in the United States is following what requirements are there for the radiologists, that we have to be board certified. We have to get our training like they need from an ACGME. We need to get from a CAMPEP certified residency. So the way things will improve is if you put things into practice or laws into practice that say this profession needs to be involved and these are the educational requirements and this is what they need to do. If you don't have that, then it doesn't matter how many people you train. They're just going to be sitting there twiddling their thumbs because no one wants them to be involved. So I think it has to come from them. And this is a situation also in India. I go give talks over there too. Diagnostic physicists, very few. Oncology physicists, many, because that's required for taking care of patients, right? Until the regulations, the people who make rules and laws about testing or whatever decide that the physicist is important, it's not going to happen. How much ever you and I, we can talk till we are sore or we lose our voices, but no one's going to listen unless it becomes a requirement. And which is what accreditation has done in our country, in America, and Joint Commission. They have really given importance to the medical physics. And I can't imagine, how can you adjust protocols without the physicists? They're the ones, the technical experts. You need them to understand how things work in a scanner.
I think it's progressing. Like in Thailand, we start training diagnostic physicists for like 10 years, and with the Joint Commission, the international version, they require the patient dosimetry. So a lot of private hospitals, they start to hire diagnostic physicists. But for the government side, mainly we work in the university hospital. I think similar to what the US do.
Right.
Yeah, we still have to a lot of things to catch up. That's all.
It'll happen.
Yeah.
So you say like the residency part for the medical physicist is like a clinical attachment, right?
So now the requirement is that after your master's or your PhD, you have to do a 2-year residency program, or if it's a program that also offers research option, it's a 3-year, before you're eligible to take the ABR exam, just like for you guys, for the radiologists. So now the people graduating, If they don't get residency slot, basically they have to find some way of getting board eligible. And unlike for radiologists, there are very few residencies. There's about 30 residencies for diagnostic medical physics in the United States. We are starting one. I don't have approval yet, but we are going to start one. We'll have a resident next July, hopefully. But we need to have it, because how are we going to train the future of our profession if we don't have residencies? Sam, do you have one? You don't have one. Well, I'm going to work on you for the next 10 hours that I have with you in this week. And we need to have more residencies to train the future of our profession. Otherwise, it's going to be gone.
Can I come back to like a Thai situation about the protocol reviews? Dr. Panrutai may be able to tell us about the protocol things. Because when I work in Thailand, the one issue is we have like maybe 10 protocols on like maybe one study, because based on the radiologist preference, I like that one, I like this one. So that's why we have like a tons of the protocol. Maybe Dr. Panrutai can comment on that things too. Yeah.
Most of our radiologists think about a CT protocol already, how many phases, and how much the slide thickness they would like to see. They think that the detail in the protocol setting belongs to the applicator of CT vendors and our technicians. So it is quite difficult, and when we want to know about the dose, and we say it's too high or usually too high, and we want to reduce it, what we do is like we look at the kV and the mass, only that. We don't go into the details, because we don't deeply understand that whether we can increase or decrease the pitch or not. It's just theoretically that we learn that if you increase pitch, the dose is lower. If about the collimation thickness, if it wider. But different machines work different ways, and we cannot understand that in details. And if we ask the CT technologists in general, they also don't know. They ask doctors how much the dose you want to lower, and they will change like the mass or the kV, and we look at that together. That's a problem, and we can ask the CT vendor to coming in also and ask to lower the dose. That is the way that we set the protocols.
Yeah. No, I can understand that. And I think that's why, in order for the physicist profession to be more visible in this country, you need champions, as we were discussing yesterday. So the radiologists need to say, we need technical experts, and the technologists need to say that too, in order for that to happen, because they realize there are limitations, that they don't have the knowledge to optimize a protocol. And so, the few physicists you have, especially if you can show that they are helping, like what we talked about yesterday, I think we need champions, right? We can't, Napapong can't go around and say, we are great, we are physicists. But unless you say, no, yes, we need physicists, it's not going to happen. We need champions to try and drive the profession up and say, we need to bring that in this country. And I hope, like people like Sam and me, when we come and give talks here, that helps a little bit. Same when I go to India, I keep saying you need physicists if you want to make sure your patients are being scanned in the appropriate manner, you're not overdosing your patients. And it's not only, that's just one aspect of our profession. There are so many other things we do that can help radiologists, technologists, and the whole department to do things in an efficient manner. We teach radiologists, we teach technologists. So it's very important that we have champions here in this country to promote the profession.
And the situation in the university hospitals are better, because more training, the CT technicians training in physics. So not really like in your country that have training the medical physicists from the start, but we select the CT technicians and get the further training, and that help a lot.
Absolutely. You know, one way of, I look at it as one way, like if I'm going for surgery, do I want my surgeon to be an expert, right? He's going to cut open my body. Would I want a surgeon to do my surgery, or do I just want Tanya to do my surgery?
I can do that.
Right?
Yeah, I have learned that during the medical school.
So how when we go out for our care, we go to an expert, right? We want trust. I want trust Tanya. How much ever I love Tanya, I want trust her to do my surgery. I need someone who is an expert at doing surgeries. So I think similarly, I think all our roles are very defined, and I can't expect you to do my job, nor can I do your job. So I think we all have to realize the importance of each of our roles and what we can contribute. And bottom line, it's not ego. The bottom line is patient safety. That's what our goal is, common goal, patient safety. We all have to work together for that.
Yeah, I think we complement each other
Exactly.
to complete the job
Absolutely.
and get things done. Yeah. Any comments? Any comments from the audience? Yeah.
She said they want the clinical physicists like you do in the US, but how can they get the training the way you do unless they go to US and training, I think?
That's a very good question, but I think there are a lot of resources out there to get training. I know Europe does an amazing job of what is the e-form, right? They have all those modules and things like that. I think that's why, again, there's got to be some kind of regulations in the country where either you develop a curriculum and say everyone needs to go do this training. You can use, there are a lot of resources out there. AAPM is a good resource, eForm is a good resource, IAEA is a good resource, but you need to define a curriculum so that every medical physicist in Thailand has gone through that curriculum to say, you know, this is the training. So Sam and I both have our PhDs. I don't know, Sam, have you done a residency? He didn't have to do a residency. It was not required when he graduated. I didn't have to do it, but I did. But our knowledge, the education we got is probably similar because in America, they make standardization, just like medical school, like radiologists. Anyone who goes to medical school in the United States gets the same curriculum, whether you're in New York or whether you're in California. Similarly for physics. So here, I think that's what you need to look at. Start with a curriculum based on resources outside the country to see what will work here for your physicists. And then you need someone saying, yeah, you need to do this in order to be called a physicist, and then you need to be, you know, be involved in a hospital. So the profession has to be recognized before you can even do all of these wonderful things, like have a curriculum and train your physicists in the same manner that we are trained.
Yeah, and I would add that part of the training of a physicist is you're being trained to think about the problem. You know, I gave a lot of examples about using TTF, NPS. I actually wasn't trained to do that when I went to school. Several years after I graduated, all of a sudden Iterative Reconstruction came out, and we were all scratching our heads wondering, why does the image look different? And so the beautiful thing about the physics training is that and it's part of the reason why it usually takes a master's or a PhD, is because we're teaching at a higher level these people to go deeper into the problem. And that's the beautiful thing. Technologists are trained to go deep into their problem, but their problems are different. They're patient-oriented. And radiologists go deep into their problem. It's obviously diagnostic related. But for us, we're trained to do the physics, understand the physics of the system. So when we immediately started looking at, for example, iterative reconstruction or dual energy, we can pull on the reserves of our training, and we can say, we need new tools. And that's the beautiful thing about physics training, is we can say, okay, I need to now re-engage and figure this out. And that's the thing about physics, is you're not necessarily a trained button pusher, you're a trained
Thinker.
Thinker. Thank you. That's a great way to put it. Thank you.
I think it will come along. Just work harder, and we just successfully got the license from the government. But the way we forward now is only compulsory for radiation oncology, and that's the first step. Imaging may be a long way to go, but I think if we have enough number of the physicists working in the field and the clinical people find a need, I think it's the way to go. And for technologists, I'm sure that you will talk about their role later. Now, technologists, we start with the bachelor degree level here, and now we have like subspecialty training for technologists already. We have like 1 year subspecialty training in CT, 1 year in
great.
MRI. So the curriculum, basically, I draft the curriculum and we do training at the Chulapon Royal Academy. So this will be more like subspecialty license for the technologists. They're quite advanced already. So the curriculum focus on like physics knowledge, how to do protocoling, and also the clinical component where we have radiologist training for the technologists. But for the physicists, I think like if we want to have clinical physics like this, we need to have the proper standardized curriculum to train them. And I think that's going to be a next step. We already had the residency training basically to do machine testing and all this stuff already. And I think this more clinical oriented physicists will come along.
Done for the morning session. Yeah. And the break too, right? Yeah. I like that we have a lot of like good discussions and share the knowledge and experience to each other. So we will come back. I will give you 15-minute break. We will come back at 10:45. Yep. Thank you. Hello, welcome back, everyone. สวัสดีค่ะ welcome back. We have a very fruitful discussion in the first session about the optimization role for the radiologist, and then we are going to continue for the role for the physicist and then the technologist. So, welcome, Dr. Kalpana Kanal.
Thank you. All right, so everyone had a good break. Let's continue the conversation. So a few of the slides, again, to remind you, I'm going to repeat, and then we'll talk about the role of the medical physicist. Again, a protocol, very important. You can have simple to complex protocols. What are protocols? They're basically a list of things you have to do on a patient on a CT scanner. And it's incredibly important, as I mentioned in the previous slide, that they have to be uniform across different sites based on indication and body habitus. You know, you can't use the same protocol on a 5-year-old versus a 50-year-old. So you need to make sure your protocols are tailored and uniform. I discussed the importance of management and review of protocols in the first talk, and in America, it's actually required by the American College of Radiology Accreditation Program and the Joint Commission. And I also discussed how important it is to have all three professionals, radiologists, physicists, and technologists be part of the protocol review because we all bring different expertise to the team. So I'm just going to skip a little bit over some of these. And now we'll start talking about what is the role of the physicist in particular. So physicists play two different roles. One is when you have a new CT scanner. You know, most sites rely, as you mentioned earlier, on vendor application specialists to optimize your protocols, right? That's what somebody said earlier. You're relying on them. Many hospitals do not have in-house physicists. They use consultants who may or may not be involved, or they use technologists like over here. So that's where I think it's very critical to have a physicist, because the protocols that the scanner has when you purchase it, it is set to give you really good image quality. That means translation, high dose. And you really need to tailor it and customize it to get optimized dose for your facility. So in the United States, Sam and I are in-house. What I mean by in-house physicists, we work only for one group of hospitals, and we are responsible for everything. But there are consultants, our counterparts, who go like a consultant would, and they go and, you know, work at many hospitals. But all they do is mainly testing machines. They might be involved in protocol review, but not to the detail that Sam and I would be in a hospital. So what's our role? Well, we have a lot of responsibilities. Not only when you buy a scanner, we also, you know, advise in what scanner to buy, but then as far as protocol review is concerned, we want to make changes to CT protocol acquisition and recon parameters. As I said, you buy a new scanner, and if you use this old protocol from the old scanner, it does not make sense. So you want to optimize what the bells and whistles are. As Sam mentioned, if you have AI available, you want to use it, make sure your radiologists understand it. And so you're changing your protocol to adapt to new features on your scanners, or you may create new protocols depending on the features of your scanners. You optimize the dose, and you compare to external resources such as the literature or the ACR dose index registry data, which is what we have been talking about all week. You know, the technologist doesn't do that, the radiologist doesn't do that. It's typically the physicist who will compare dose from your existing protocols to external resources. This ensures that the site dose is in line with established reference protocols. So if I'm doing, you know, giving 90 milligray for an adult head versus everyone else in the country giving 60, there's something wrong with my protocol, right? So you need to compare. You cannot just say, okay, yeah, I've optimized my protocol, it's 90, it's perfect. Well, you don't know it's perfect because you have not compared it to what's out in the literature. We also play a very important role in educating our radiologists and our CT technologists on the function of the various CT scan options on a scanner. For example, how automatic tube current modulation options drive the dose and image quality. So on our Siemens scanner, the automatic tube current modulation has different curves. You know, there's weak, average, strong. How you set the curve drives how much MA you're going to use for a patient. And so depending on the patient population, whether you have obese patients or young patients, you may want to change that. Those are the technical features that we, the physicists, are educated about, and we can educate the technologists and the radiologists about. And I will say, without a doubt, and I'm sure Sam agrees with me, that we could not do our job if we did not work with the technologists and the radiologists on any issues or changes that come up. You have to be part of the team. You cannot work in a silo and say, what I am saying is the law and you have to do it. No, you have to work with your radiologists and your technologists. A technologist really is your best friend. You need to get on the scanner, you need to talk to the technologist. You want to make changes on the protocol, you need to work with the technologist. They really have to be very involved in what you're doing as part of your job. Again, I'll mention this is our University of Washington medicine system. We control all of these, makes my life very difficult when I'm doing protocol review. So how it was done, I will talk about that before how we changed it when we took it, this became more regulated. So this was physicists initiated. We initiated this, email to section chief for each section. Very tedious and slow process because, as I said, everyone's busy and emailing and telling them, let's do protocol review, like no one wants to do it. So it used to be very tedious, very slow. Complication also was trying to do it across many sites. Do I do it in University of Washington only? Then do I do it at Harborview separately? Do I do it at my children's hospital? Trying to figure all that out. You want to have a physicist, a radiologist, and at least 2 lead CT techs from each site, that one from each site. That's how we used to do it. And review paper copies and make changes, which is, again, very tedious. And then the lead CT tech supervisor would implement the changes on the scanner. This is the way we used to do it. Everything was slow, tedious, not very efficient. And sometimes we used to have meetings, sometimes we used to not. So I said, no, this does not work really well with that model. How it is done now, as I keep mentioning that for change to happen, you've got to have some kind of regulation, right? So in America, the American College of Radiology accreditation program has a quality control manual. In that, they enforce CT protocol review more consistently. So once it became regulation, and in many states in America, the Department of Health regulates that you have to do protocol review. So once that became more popular and more consistent, everyone started paying more attention to protocol review. So what I did, this was about maybe 10 years ago, I wrote a letter to radiology leadership, and I highlighted the following. I highlighted the role of the radiologists, the physicists, and the technologists in doing protocol review. And I mentioned the benefits, as I mentioned earlier, of reviewing protocols on a new basis. You want to make sure you're eliminating protocols you don't use, making new protocols for new technology, and so on. And once I did that and we got buy-in from leadership, again, working just as a person in a department and trying to enforce change will not bring change. You've got to have support from top down, from the leadership who believes in what you're doing. They need to say, yes, this is going to be done, and then you need buy-in, and that's how change happens. So once we started doing that, things became a lot easier. As I showed you this earlier, we have more consistent data online. I showed this in the lead radiologist slide. This is my schedule I want to show you for physics. So here is, I told you we do body imaging lectures, and under body I have GU protocols, abdomen, liver, pancreas, dual energy protocols, vascular imaging. That's what we have divided ours. So for 2022, I had 3 meetings, actually. We managed to do all of them in 3 meetings for body protocols. Neuro, you can see I've put to be decided because I have to now schedule it for November. For chest and cardiac, it's coming up in a couple of weeks. I have chest and cardiac protocol review. MSK, I did it in August, and then trauma and peds to be decided because it's not due till November. So for me to keep track of all this, I have my very simple spreadsheet, but I just go and make sure we are doing this protocol review, formal protocol review once a year. But continuous protocol changes happen also, just the formal ones happen once a year. What are some of the things as a physicist I would look at when I'm looking at this protocol sheet, I would look at the things that impact dose, right? The KV and MA control. This is a dual energy protocol, so everything is manual GSI for GE. I would look at what is my Acer set up at, what are my slice thicknesses, and then, that's what my goal is. And what I do before the meeting is we use our dose monitoring system and look at what the doses are for all our protocols for that section. And if, as we are reviewing, I will say, okay, we need to do something about this protocol because our doses are higher. Or I would say our doses are lower than the 25th percentile. So you have room for improvement if you want to improve or the image quality. So my role is very specific to the dose and everything. Even though I run the meeting, I'm the one who displays the protocol. My goal is really more to talk about dose, and I point things out to the radiologists and technologists to make sure that they're paying attention to the contrast, to the reformats, and so on. Besides doing it this way, there are other options for protocol review on a regular basis, right? So, one thing I want to talk about before I talk about that is, once we do protocol review, how do we make sure that the change is implemented and everyone knows about it? So we have what's called a CT change control form. So it's pretty old, what I put in here. The proposal was reduction of max phase doses by 20%. And actually it was requested by me. And I said, we want to be within the 75th percentile of the ACR recommendation. CSIC is a meeting that we have for CT every month. And so this was who does this impact patients? Yes, does this need discussion? I said yes. And then, there's a whole approval process, when you want to implement it, the date of approval, who will implement, if we deny the request, why we denied it. And then who does the implementation go to? Who needs to be informed? Well, the CT techs need to be informed, radiologists need to be informed, residents and fellows need to be informed, and I made sure there was a line there, communication to physicists need to happen, so on and so forth. So we had a very formal process for implementing any change discussed during protocol review with these forms. And then this would be sent out and everyone could then know that this is what's going to change, starting whatever date. And if this happens during the formal review, but during the year, if I want to change something, I just do this and I send it to the email address, CT Change Control, and then we make a decision either through email if it's simple, or we kind of have a quick meeting to talk about it. So not only doing the protocol review with everybody, but then actually having a formal process of implementing the change is incredibly important to do as well. Besides looking at doing this in formal setting the way we are and we sit, there's also other options for protocol review. So for example, we are now testing a software by General Electric that's called CT Protocol Management. It's installed on our scanners. It has potential, but it's still new. What is the benefit of CT Protocol Manager? It's basically all online. It's on the scanner. You can pull it up on the cloud. You can make changes instantaneously. And as soon as you make the change, you can send it back to the scanner. So instead of having the meeting, then you have the form where we're making the change. Then the technologist takes the form. She goes to the scanner. She makes the change. Then she has to send that and go and do it on every scanner. The protocol manager, it would be a fantastic solution and efficiency where you would just make the change as you're talking about it and say, send to scanner. And then depending on what scanners, you could send it to all the scanners you want. So we are right now, I have a grant to look at this. I've had it for the last 2-3 years, and they keep updating the software, and we keep evaluating for them. It's still new. And I think, Sam, you mentioned things like team play and things, but I don't know if they do protocol review for Siemens. But I think this is becoming common. I know GE has it. I don't know if any other vendors have protocol management. Philips does too. So because this is such a tedious process, vendors are looking for efficiency. So the advantage of doing this would be to compare protocols online for different scanners. You can review, you can make changes, and hopefully implement from manager, the CT protocol manager, straight on to the scanner, which would be fantastic. Now, there are a lot of challenges with this. It's not as easy as I'm saying it is, because if one CT scanner has a different software version than another CT scanner, not compatible, right? So things like that. And if I have GE, one GE, and one Siemens, or one Philips, it's not going to send to the other vendor. So there are some things that GE still needs to work out, but this is a great also tool to compare your protocols and also document when you made changes. So if I change the KV today from 120 to 140, if I have an efficient way where it's saved in the cloud and I know what date I changed it, suddenly if I start seeing crazy numbers in dose and I know this is what I did on this date, this is when the problem started, let's go and reset it. So it's a more efficient way of doing protocol review. Other thing that we do throughout the year, so I mentioned the formal protocol review, which is with the radiologists and technologists. But as a physicist, I have my dose monitoring system, and I'm sure this is for GE Dose Watch, and I have hidden here the patient information, but I get an email. I get about, in a day, I get about maybe 50 emails in a day from Dose Watch on anything that might be a slightly higher dose than the regular alerts. So what this is telling me, this is for this patient, abdomen, the CTDI wall was 43, when typically the CTDI wall is somewhere between 28, and GE is a little weird how you put the alerts, but you have to at least have it a little different, so you have two different differences between warning and an alert level. So this, for some reason, the dose was very high, 43. And so this is something I get on email too, every day, right? If I have, and that could be many reasons. The patient is obese, patient was not centered, maybe it says abdomen, but maybe it was actually a different protocol. What I'm trying to point out here is you're kind of doing protocol review on a regular basis by looking at these type of alerts that you get and figuring out, oh, is there something wrong with this protocol? Do I need to change anything? And so on and so forth. So this is something Radiometrics, I'm sure, also does, right? It sends email. So you're kind of looking at it and saying, hey, I need to look at this protocol. I've been getting a lot of alerts. So there's another way you're doing protocol review on a regular basis. Here is the second half. So it's the same patient, and it gives me more detail. It tells me what scanner it is, one of my Revolution CTs, which site it is, what protocol it is. It's a CT abdomen pelvis with contrast. I also have the ARPID assigned, and I can look at that. So it also gives you BMI of the patient, 111 kilos. That is a big patient, right? I don't have the age of the patient handy, but you can see then very quickly look at this and say, yeah, this might be okay because the patient is big, or say, oh my God, something is wrong here, and keep an eye on that to make changes to that protocol on an ongoing basis. The other thing, as we have mentioned throughout the week, is comparing your protocols over quarterly basis, semi-annual basis, however you want to do it, to the dose index registry. So this is for one of my hospitals. I have it, my names for my protocols. The N is the number of exams. And I want to compare my doses on a regular basis to all the American College of Radiology sites. But Harborview is a trauma center, so I also want to compare it to trauma. Because, you know, in trauma, as I mentioned previously in the week, sometimes you're worried more about saving the life of the patient than radiation dose. So, you know, if the dose is typically maybe a little higher than other sites, that's why I also want to compare to trauma. Even though in this case, it doesn't look like lot of differences between all ACR sites and trauma. But basically you want to compare. So you can see here head max, which I showed you earlier, much higher than anything else. Again, max face with IV, because the way we do max face is a little different. They do the head scan first, then they do the max just based on what they're trying to do. So our doses have always been high. And really the idea of comparison is say, what's going on here? I mean, this is twice what ACR has. That's because we are doing things differently at our trauma hospital than what other sites are doing. So things like that you want to do. Besides the formal setting, these are some of the things you can do to do continuous protocol review. A very important resource, I think, which is very helpful for physicists is AAPM on their website has protocols that you can compare yours to. Those are all vetted. They are reviewed by, I'm on the committee actually. They're reviewed. We have vendor representatives on the committee, and you can compare your protocols if you want. You can also see over here, I want to show you because this is a good resource for you guys to have. And I don't remember if this is open source or do you have to be a member to access it? Sam, do you know? Those open, but are the others, the CT dose track and education slides? Okay. Okay, so I asked the question whether this is an open source, so even people here in Thailand can review it. And my colleague here, Dr. Brady, said, yes, you can. So great resource for all of you, and outside the US, there is a role of our physicists. What do physicists do? CT dose check, which I will talk about when we talk about the technologist role, protocols, looking at lexicon, the ARPIDs and RADLEX. The CT dose education and the CT automatic exposure control education slides are amazing. If you want to understand how each vendor uses their automatic tube current modulation and how the dose works with respect to that, these are great slides. And they keep getting updated every few years by this committee. So again, a fantastic resource for anyone who needs a resource that you can look at. So when you go in there, you can see here when I clicked on protocols, there aren't a lot of them. There are just a few. So there's pediatric, there's adult, but they have the bread and butter protocol. So there's adult head, there's perfusion, adult abdomen, chest, lung cancer screening protocol, which in the United States, you have to be accredited to do that. It has very specific dose requirements, very low dose. Why? Because it's a screening exam. That protocol, CT colonography, and they have some pediatric protocols. So when you click on one of these, it will throw up different scanners and all the parameters, the technical parameters you need to, and it also will give you what the CTDI is based on that. So if you over here in Thailand have a Lightspeed 16 for GE, you can compare your protocol to what's listed on these vetted protocols and say, yeah, you know what? Mine are okay. I kind of agree with what AAPM has. Or if your dose is really high, you can go here and say, yeah, this is what we need to do and make a change and compare your protocols to that. So again, very, very wonderful resource for people who don't have a lot of resources to compare your protocols. The other really important part that physicists are involved in, and this really we work a lot with the technologists on, is something called CT dose check. So what is dose check? I don't know how many over here know about that, but in the US it came out a few years ago. It's a standard basically that has been collaboratively come up with between MITA, which are all our vendors, manufacturers, and MITA is kind of the body that works with vendors to come up with these standards. And what was the goal? The goal was to increase active awareness of standard CT dose metrics and introduce tighter controls to mitigate singular overexposure events. So the idea is, let's avoid what happened in California with that child, where he got all that before we do an actual scan. So there were two terminology, and Sam talked about this briefly, I think on Tuesday, that you have to set up on the scanner so that you catch a problem before you scan a patient. So that's why I call this also part of protocol review, because you're going in there, you're setting these standards where if you exceed the standard, that it'll give you a little message saying, do you really want to scan the patient with this dose? And then you are being proactive as a technologist to say yes or no. So this is something that the physicists are involved in. We come up after doing all our dose monitoring. We are the ones who figure out what notification value we want to set it up. And as Sam mentioned earlier, you don't want to set it up too low that the technologist keeps getting a warning, nor do you want to set it up so high that you never get a warning. So you kind of have to have that balance to make sure you're doing the right dose. And then there's a global value, which was by FDA standards in America. It's 1 gray on all scanners, but you can reduce that if you want as well on the scanner. So the alert value, you do 1 series. You do a second series, you do a third series, the FDA recommended alert value is 1000 milligray. And this one, even though you're doing many overlapping parts of the patient, you haven't reached that value yet. But that could potentially happen. So that's what that big global value is. If you exceed it, like in this case, your series 1, same area of the skin, series 2, same area of the skin, series 3, now you have exceeded this. It is not going to let you scan the patient. It's going to say a dose alert value will be exceeded from your scan that you have picked. You need to figure out why this is. And this is where we come in, where we set the value, but we really work with the technologists on this because they are the ones who are scanning the patient. So they have to log in and say, yes, I know the dose is high, but blah, 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 whatever the reason is, I'm going to go ahead with the scan. Or they would go, oh, I think I did something wrong here in my dose. So that is really the idea of the alert value. Stop, think, don't do 151 scans like that on that poor kid, and say, do I really need this dose for the patient? So this is in a way, a proactive way of doing protocol review, right? You're making sure that you're not scanning a patient with a high dose. And only certain individuals have the privilege. So it's obviously the technologist who's running the scanner, and it's typically the lead technologist who can override this. And physics needs to know about it. Why? Because when we test annual testing, we are almost always going to exceed some level of dose because we do so many repeat scans. And so we need to have privileges and go in and just say QC. That's why the dose is high. And then this gives you an idea. How do you set up this notification value? So these are all our head protocols, and the varying doses. You can see some are 94s because it's combining 2 different type of protocols. But typically it's about 44. So you as a physicist have to figure out, and the question mark is, what threshold do I want to set this at so that we catch exams that are unjustifiably high, but not too low that we are triggering on every exam. The technologists will kill the physicists if we set it too low, right? Because every time it'll come up on the scanner. So that is something then you have to look at your data and figure out what your average or median doses are, and then come up with some kind of methodology. Do I want to set it at the 90th percentile? Do I want to set it at 20% higher than my average? That's up to you, how you do it. That's between you and your technologist, and you figure out how you do it. So here it shows you that we set up for our regular head here, we set up our alert value to 50. So if there's ever a dose, ever a scan that's being prescribed on the console, and the tech, she might get an alert because it was over 50, that's when she'll get an alert. Hey, do you really want to scan this patient with this technique? Because typically you have 43 and now you're getting 55. So what's wrong with that picture? So this is a proactive way of making sure you're not over-radiating your patients. So this is a requirement in the US, and I won't go into a lot of the detail. This is a presentation that we made at AAPM a few years ago, but it really is not easy to decide what to set up that threshold is. You could just go with one number, but then you might have problems. You need the physicists and resources to try and figure out where's the best place to set this threshold to make sure that the technologists are not getting burnt out with all these alert levels, and you're making sure your patients are safe and not overdosing. So the AAPM came up with some notification values. So they have some high numbers, as I mentioned yesterday. They have adult head is 80, which is actually the same as the ACR accreditation value for passing a head exam is 80. In practice, none of us are around 80. We are more like between 40 and 60. 80 is too high, in my opinion, for a head. But this is a good thing to set it at, because then that's when you get an alert and you still catch like what's going on. And then depending on the body part, torso, pediatrics, 50 and 60, of course, Sam's not going to adhere to this. He's going to make it more like 30 and 20 or something, right, Sam? These are guidelines, But you can be as conservative as in Sam's case, where he says, no, yeah, that's what they recommend, but I am going to do much more conservative numbers. Or you can go a little bit more liberal and say, okay, nah, it's all right, we'll set it at that higher value. But AAPM gives you some guidelines on how to set this up. And all scanners, probably after when did 29 come out? Probably 10 years ago. So I would say any scanner made in after 2010 probably has this feature available. So your scanners, I don't know how old they are in Thailand, but you can set this up so that your technologists, with the help of the physicists, set up these, and that way you do not by mistake over-radiate a patient. So this is just showing you could do it an easy way or a difficult way and do all kinds of things to figure out those notification values. Once it comes, notification value, we had to figure out, what do you do if you get an alert? That's what I'm trying again to show you here is the teamwork, right? So we are the ones, the physicists, who come up with the NV value. We go and program it in the scanner, which is what we typically do. But it's a technologist who will see it if they get an alert. So then what we decided to do at our site, we said that whoever is a radiologist on call that day or whoever's the attending that day in the reading room, you need to confirm with them whether you can go ahead with the scan or whether you need to readjust the parameters. Because just saying, oh, it's okay and let's go ahead, defeats the purpose of doing it. So you need to make sure there is some follow-up and you're closing the loop to make sure you should be doing that scan or not. If the radiologist said, yeah, fine, the dose is high, but we need this, you go ahead and scan after approval. But you have to document the diagnostic reason. Metal hardware in the patient, that's why we are increasing the dose, or we are doing whatever the reason might be. And then you have an audit tool on the scanner, which we look at periodically to make sure that our alert values are making sense or not. And you can kind of do all kind of math on that and check, okay, yeah, here was the NV we set up for the spine, but looks like the projected is more than that in some cases, and the differences and how many alerts we have, and we can adjust the value based on how many alerts we get. So it's kind of a trial and error methodology of figuring it out and doing that. But the physicist can understand that. They can put it on the scanner, and then the physicist does a lot of education of the technologists so that they understand what happens when this comes up and what's it telling you to do and things like that. So in summary, for physics, again, we do a formal protocol review. You need to work with the technologists and radiologists. We are responsible for making changes to the CT protocol acquisition. If the radiologists tell me, I really think this image is too noisy, we are the ones telling them, okay, let's do this. Let's adjust our automatic tube current modulation or the noise on this image to make it a little better, and do it in baby steps. As Sam mentioned 2 days ago, you don't want to make an abrupt change because radiologists will totally scream. You need to do baby steps so that they don't know. You need to do it in stealth mode so that they are not noticing those changes in image quality. And you want to optimize dose and compare to external resources. We have been talking about this all week. And the other very important role I think the physicists have is we educate our radiologists and our technologists as to why we are doing things the way we do. We give in service to our radiologists, we give in service to our technologists, we give in service to nurses, because we are the technical experts. We understand how things work on the scanner. And you do need to work with your lead technologists and radiologists on any changes that come up. You want to be part of the team. And there are many other resources. AAPM is a fantastic resource, ACR CT dose index registry, and then your own dose monitoring software. In your case, it's Radiometrics, to look for problematic protocols throughout the year, not just during formal protocol review. Thank you.
Thank you so much for the excellent talk, as always. Any questions or comments from the audience online and also on site? After the last talk, Napaprong, I have one question for you. Do we have that any dose alert set level in Thailand, and how do they report to anyone?
We do as individual hospital where we run the dose management system. So the hospital that I work, we do set this alert level, basically like use the APM alert level. And because first we started with our DRL, but a lot of scans get alerts. And also when we set up the alert for fluoroscopic procedures like skin reaction alert, first we set like 2 milligrams and then we get like tons of them. Now we shift, you know, it depends on like what we do. We want to do at dose Acurma at reference point, or we want to do really do the skin dose. So it just depends.
Depends on the hospital.
Depends on the place where they have the physicists to do it or not.
So which means like let's say like for the whole country, how many hospital that have a dose alert level
don't know.
set, or
At Chulalongkorn you have?
I mean CT for like setting the level to alarm.
No, it is not like that. It's like if we set the alert for CTDI volume for brain, if we set the alert at 80 milligray, in any case, if the CTDI volume exceeds 80 milligray, a person who is responsible for the dose management program will get the email notification. That's what you mean, right?
Yeah, no, but I think what Tanya is asking is about on the scanner, what I showed you, the NV value,
Normally
whether
they
you have it set up for your protocols.
Yeah, they have it.
I mean, like every hospital with the new CT scanner have like that dose alert level set, right? But that is like maybe the first step, and then the second step, like
Sometimes-
email someone.
No,
maybe.
no, that you need the dose management system. But a lot of time technologists just click ignore. It's like MRI when you have the high SAR level, just ignore.
Oh, now how did you teach your student like that?
No, because we can't proceed with the scan.
Okay.
It's locked. She said that when they, in case they have the normal, the up-to-date scanner, I think it's the compulsory, like the machine needs to meet the FDA requirement or NEMA standard requirement. It's already integrated in there.
Yeah, we have to do it in the US because it's a requirement. But I wouldn't say that everyone does it. I would say that, yeah, some will set it high enough so that you don't keep getting those alerts. It kind of defeats
that
the
alert is
purpose.
very
Because,
high.
you know, the way when I explain to the technologists, I say the reason we are doing all this, we don't want to be on the front page of the Seattle Times, right? Saying that we overdosed our patients. We want to do this for a patient to make sure we don't over-radiate them. And so that's why that alert level we pick, we evaluate it every 6 months. And if we're getting too many alerts, then we make that notification value a little higher because most of our patients are at that dose. So you want to find that balance between too few alerts and too much alerts, you know, because you don't want the technologist getting upset that, oh my God, I keep getting alert. You don't want that. But the idea is, again, make sure you are catching cases that the dose is too high.
I think we can configure the alert level.
Absolutely.
Right? Yeah.
You can do whatever you want with that alert value.
And if you are getting a lot of alerts, the question is why?
Why? It's a question.
Hold on.
In case that you get the information of alert in terms of the medical physics, do you have to do like a review that kind of alert?
Yes. So I think I can show you really quick. Let me go back to that. First, let me wear my glasses.
While she's looking, you can also, on the scanner, all the scanners will be able to run a report on the notification values. So the doses go to the dose monitoring software, and those are completely separate alerts that'll go out from email. But if you ever want to, you can go onto your whatever vendor scanner, and usually you go into the service side or the administrative side, and you can run a report, and it'll actually export all the times it exceeded the level, the dates, the times, and why.
And that's what I was trying to say, which I didn't do a very good job of. The audit tool is on the scanner. You can dump a report of the how many exams alerted. And then what we do is, like, this is after 3 months on one scanner, and it shows you what our NV was and what actually was a scan and how many cases we were actually higher 8 or 9% or 10%. And then we look at it, and then if we see that, oh my God, for this particular protocol, we are alerting 20%, that's really high, we might go and tweak our alert value to be a little higher. So in this case, we put 30, but we keep getting 32. So then next time what I did, I went and changed that 30 to 35 or something like that. So you adjust a little bit based on that, but we do have to audit. Otherwise, there's no point doing this. And that's something, again, I think the physicists can easily dump out of the scanner. You do it, then you talk to the technologist. Hey, I'm getting a lot of these alerts. Do you kind of agree that we should, you work with the technologist, but then you go and then change the setting. Or sometimes a technologist will reach out to us and say, hey, we are getting too many alerts on this protocol. Have you guys looked at it? So they bring it to our attention sometimes, saying we're getting too many alerts, and then we'll go and change it. So that's why you have to work as a team. They're the ones at the scanner. We are not. They tell us if something looks a little different.
Can I say that there is like a 2 alert level? The first alert level is like at the scanner, if the technologies can proceed the scan or not, right? And that may be like the preset from the vendor.
No, we said that.
We said that. Okay.
Yeah.
So which means like according to what Napapong said, like the first step that preset the set the level from the scanner that from the vendor, according to what Napapong said.
In Thailand, the physicists don't set that it's preset value from the vendor.
I doubt it very much. Really? They should not be presetting anything.
Yeah.
They don't know your doses.
If you buy a scanner, it will come without any.
Yeah.
So they may be putting it in based on their knowledge.
Yeah. I think it's a default from the vendors.
So that's their suggestion. So if you trust them, that's your
I
choice.
don't. I would be very careful. If they come with anything default, you need to verify that it makes sense.
So which means that is like the first step. The ideal situation for the first step on the scanner should like have some value set up by the physicist, but the situation in Thailand may be a little bit different.
Right.
So Napapong gonna look into that maybe. And then the second step for the dose alert level in the hospital who has like a dose monitoring system, right? If we exceed those number, our data sent to the medical physicist in that hospital.
Yeah, I mean, they both work simultaneously. They're not serial, what you're saying. I mean, it's all happening at the same time.
Yes, but it's like maybe like a 2-step, 2-level check.
You could do that, yeah. One thing is doing at the scanner, and one is, whatever you're setting up for your dose monitoring system is doing, so.
When we install the dose management system, we instruct the vendor. They have the application specialist, mostly my students. So I told them to do the preset values for the customers. Like we set up the DRL based on like local DRL, and then I told them how to compare the value. But at the end, there should be someone who knows about the dose to manage this. So this is the thing. And we have a lot of problem when we first install numbers of dose management software, especially like in a private hospital. So they have like hospital chain. One chain has like 10, 15 hospital. So and then they had a competition like which hospital has the least dose something. I just passed out. And one hospital, they even want to report the effective dose to the patient.
Oh no.
It's like yeah, this is the thing, because sometimes a person who take care of the tool must be a person who know how to use the tool.
Absolutely. And again, too much information is not a good thing, because as you said, if you're giving out effective dose to your patients, they don't know what that means. So you don't want to do that, and you have to be very careful in what you're communicating to your patients.
You know what I did? They asked the vendor to put like banana dose equivalent.
Huh? What is banana? เทียบรังสี
Yeah, because
กับ
we eat banana, we get the dose. So they
it's
compare like how many
natural
banana you eat. Like I pass out, you know, like what happened in this world?
Yeah, but it takes thousands of bananas to get to a CT scan.
Yeah, otherwise we would all be in trouble if there was a lot of dose in a banana, right? A lot of radiation in a banana.
พี่
Lucky most of the vendors, the application specialists were my student before, so they call me.
Okay, so พี่โออาจารย์นภาพงศ์ one more question for you. So for the, you said like for the hospital that has like a dose monitoring system, there is like another setup where you and send the email alert. So right now, because a majority of the hospital in Thailand does not have the medical physicist, is send it up to you directly or to whom?
No, it's up to them because I'm not gonna work for everyone.
Okay.
That's
but
why I said you have a tool, you need a person who know how to use
Okay.
the tool.
Okay, sure. So if they don't have that person, okay. But we will try our best to help them, right? We will try our best to help them.
Most of the time they would contact us, like
Yeah.
they would ask what to do.
Yeah, absolutely. I mean, you don't have to go to every hospital and do this, especially if you're not responsible for that hospital, but you can advise and you can direct. Here's a resource, look at how to do it. This is the way we do it. If they have the same machine you have, the same type of population, you can even share your NV values, and they could put that as a starting point. There's a lot of ways to help indirectly, like now how Sam and I are come here, we're giving talks, right? It's indirect, but it's still you're trying to guide people and give resources and give information. I'm not responsible for Sam's hospital, he's not responsible for mine, but we can share ideas and resources.
Okay.
I
You
think
need
Sam's
something?
ready for lunch.
Hey,
All right,
one
I
more
will go
talk.
really
One more
fast.
talk. One more talk about
Yes,
the
one more
technologies.
talk.
Yes. Mhm.
Okay, so let's get started. Really great discussion, guys, and that was really the idea of doing this. Okay, so let's talk about the role of the CT technologist or radiographer. Again, I have the first few slides. I always want to have the same common slides to remind you guys why we are here. We're trying to manage protocols, have consistent protocols. It's available in the United States. We have to do this. And I think everyone should do that because we are giving radiation to the patient. So we want to look out for the patient. So we talked about the radiologists, what their role is. We talked about the medical physicists, what their role is. Let's talk about the technologists, who are also incredibly important in this review of protocols. So why does a CT technologist need a protocol, first of all? Well, it simplifies their workflow, right? They can't sit and build protocols as a patient comes in. So if you have a protocol, you pick the appropriate protocol, you hit the button, and you scan the patient. It meets the clinical indication requirements and then has to be set for appropriate dose, radiation, as well as contrast. And you're standardizing protocols across the enterprise on different scanners. So if a patient came to scanner A versus scanner B, they should get exactly the same dose, depending if the scanners are the same. And of course, patient satisfaction. You need to be consistent. Remember, the person who is the closest to the patient is the technologist, because they are interacting with the technologist. They are the ones positioning them. They're the ones doing the exam. The radiologist is indirect, so is the physicist. So very, very important the way they manage patient care. So what is the lead CT technologist responsible? Well, they have to implement any changes discussed, whether it's a protocol review meeting or any other reason on scanner. Not only on one scanner, if you have 20 scanners, on all scanners. Updating the protocols online or in a book. So I had shown you earlier, and I'll show you again our protocols, and bring any issues or problems to the attention of the team, right? So we do actually have, we have a CT change control email or CT for protocol discussion, and I might get an email, like whoever's on the team will get an email from a technologist at one site saying, hey, here, this is this, we want to make these changes. And if it's minor change, that discussion can happen on email and can be implemented. But they need to have some way of communicating to the rest of the team if there is a problem, because remember, they are the frontline people. They are the ones who will see the problem first before the physicists. And well, the physicists might see it in terms of the dose monitoring system, but in terms of actually during scanning, they are the ones who see it first. They want to make sure they can make real scan time decisions, right? They're monitoring dose check alerts, hopefully, for the physicist. At our hospital, technologists are actually protocoling instead of the radiologist to save the radiologist time, and I'll tell you what that means in a bit. And then they interact with the radiologists, the physicists, billing, scheduling, and nursing. Technologists have to do a lot of things, and they're a really important key person, and therefore they need to also be involved in protocol review. Again, I'm showing you our system. We are covering tons of hospitals. Every hospital has technologists who only work at that hospital. So the people who work at University of Washington Medical Center do not go to Harborview. The technologists who work at Harborview do not come to University of Washington Medical Center. So that is, again, a little complicated because we have technologists who don't interact with each other at different sites. They might interact in asking for advice or guidance, but they don't go work at each other's sites. So again, having the protocols online is a responsibility. However you do it at your institution, having it online and just putting it on is not enough. They have to maintain it. And the reason for that is once they have it online, anybody in the department can go access the protocols. The radiologist, the physicist, anyone who has access can then go. So these has to be kept current. You cannot have a protocol online that's 2 years old and what's on the scanner is totally different. So big responsibility for the technologists to maintain this. And physics, for me, I help a little bit, but they really are in charge of this and maintaining it. I don't do the maintenance day-to-day work. One thing I want to point out, what the other thing that's important for them is, you can see here, this is for protocol review done this year. We were looking at abdomen protocols. If you remember my schedule, I had a meeting in March, and Gulnoor, who is our CT tech supervisor, has edited it based on whatever discussion we had at protocol review meeting and the date. Extremely important. So not only are you maintaining this, but every year you are editing it at the top or wherever, even if you have a front page saying that this protocol was edited on this date. Because this is something that the state regulations as well as Joint Commission will look at to make sure you're doing annual protocol review. So we have to make sure our dates are current. And they do a really good job. Our technologists, they put the anatomy they're scanning, they make all these beautiful, visually pleasing protocols, but they are responsible for everything on this page in terms of maintaining it. Again, here shows you another one, nice diagrams based on patient size. And a lot of the protocol review meetings, a lot of the questions actually are brought up by the techs, where they will say, oh, you know, for this thing, we are encountering this problem, or for these type of patients, we're encountering this problem. And then the radiologist will chime in and, you know, how do you handle, do we want to reduce the contrast? Do you guys really want MIPS? Do you really want SAG body and stuff like that? At our protocol review meetings, we have radiologists, I already mentioned physicists. For technologists, I have a technologist from every site that I cover. So I'll have a technologist from here, University of Washington Medical Center. I have a technologist from Roosevelt, East Side. Harborview is one they represent. We treat children's hospitals separately. We do those protocol reviews separately. So no one from there, but we'll have Northwest Hospital, we'll have Seattle Cancer. So the room, the virtual room is filled up mainly technologists. All chief technologists or a lead technologist. 2 physicists, I always have a backup, and maybe the chief radiologist and maybe 1 or 2 more people from this section. So it's a pretty big room. But the reason to have all the technologists from all sites, because as we are discussing change, we discuss the change for the GE scanner, but at Harborview, I have Siemens, and so we then discuss how do we make the same change as close as possible on the Siemens scanner. And that's why it's important that you have a technologist from each site and that's what I have. I either have them all at our meetings. And if they're not there, then it's tough because then they just rely on the minutes that I prepare to see what changes were discussed. But they are responsible for doing that. So then how do we communicate? I showed you one example in the previous talk. Here's another example. Communicating changes enterprise-wide, right? All those hospitals are under one enterprise. How do we do it? We do CT group emails. There are semi-monthly CT modality group meetings. So twice a month, every Thursday morning, you can bring it up. And then the change control form. And here's an example. Here are all the sites, which site did it initiated or applied to. And you have a lot of other information here. And I noticed they don't have physicists on this new form, which I need to rectify. But everything is done in a very systematic manner, but done by the technologists. They are the ones who drive implementing the change and communicating the change to all the sites. And here's another example of change control form. This was done by two technologists, and they did it with the radiologists. Mike Jam is our he's our cardiac radiologist, and so they're saying they want to change to meet TAVR CT scan specification and keeping the dose as low as possible. And then there was a discussion, and it shows here who implemented it and was it communicated to the respective bodies. If this is not done by the technologists, I would not know about it unless I remembered what was discussed at a meeting. So we have to have some way of keeping track. This is another thing our technologists do as well, this is great. The other very important thing that technologists do at our site is keeping track or justifying dose alerts. So this is from our Dose Watch program, and this is showing you a graph over different months. Justified is the blue line, orange is not justified. So every time we have an alert, like the one I showed you from email, you have to justify why is that alert there, right? So we have all these codes. I think I mentioned it yesterday. So DW01 is high BMI, SCO3 is multi-phase exam, SCO6 is where the patient had their arms down, or some other reason. So we worked with the technologists to come up with these codes, and in DoseWatch, this is at one of our sites, they log in, and this anything in red here, you can see that 36.4 was the alert. Our notification value is set at 34.2, according to DoseWatch this is. And yeah, they justified it. The reason was patient was big, things like that. So this is something we rely on our technologists to do as well. The other thing that we are trialing now at University of Washington Medical, at one of our medical centers, is having the technologist protocol. So what do I mean when I say that? So at our hospital, and I'm sure at even maybe Tanya, your hospital, and Sam, your hospital, radiologists protocol a week in advance for patients coming next week what protocol should be used on the scanner for a particular clinical indication. So at our hospital, we do that about a week in advance. And that is very time consuming for radiologists because they're trying to read as well as they're trying to protocol. And you know that. So what we decided to do is for some easy studies, we wanted to put that on the technologists because they can do it as well as the radiologists can. So it's less time required than for the radiologists. They don't have to spend so much time doing it. Maybe there'll be less errors, reduced stress for the technologists that the protocoling was done and they're not still waiting for the radiologist to protocol, and it also improves the workflow. So we tried that. We are still doing this at our hospital. So here are some examples of simple protocoling guides: chest routine without contrast, what's the protocol type, protocol code, and what is the indication. So our technologists did a great job of preparing these kind of tables for the different indications. And they can then very easily pick up the protocol they want. So again, no offense meant to the only radiologists in the room, but here is just showing you some idea of advantages of technologist protocoling. So here is the study. Here is technologists, the amount of time they took from order to study completion, number of exams, and this is for the MD. So the texts are very fast, and here's a number of protocols that they protocoled. So 0.86 compared to 1.69. As I said, no offense meant to the radiologists, but they have many things going on, and they take much longer to protocol than the technologist does. The other thing they also wanted to compare is if the technologist is protocoling compared to the radiologist, what is the error rate? Would they both pick the same protocol? And this shows you overall, there was more than 6,000 studies. There were 21 errors made by the technologists, which is only a 0.34% compared to MD errors, which was, it was a much smaller number, about 1.9. The point of this is not saying radiologists better or technologists are better. The point here is technologists can do some of the things that take radiologists longer to do because of their clinical burden. And technologists also, that reduces their stress because then they know what protocol they have to use. So really a good way to use the technologists and their knowledge for protocoling, and that's what we do at our institute, at our hospital. The other thing, we have asked our technologists to help us because this is something that we, the physicists, brought up. It's very annoying when you go to DoseWatch or to Radiometrics and you see 10 variations of the same protocol name. Very, very annoying, right? Because then, do I look at CT head from this protocol name? Do I look at CT head dose from this protocol name? So we approached our technologists and we said, you guys are doing too much free texting. We need to have consistent terminology for naming protocols, irrespective of what scanners we have. Okay, so we initiated this project. We got the blessing of the director of CT, the radiologist. So we're going to work with the technologists on this, and then we'll pull the radiologists in. So we started working on this in 2019. Then COVID happened and kind of went on the back burner because technologists didn't have time. And then we picked it up again last year. The idea is standardized protocol names on CT machines, or standardized reformat labeling as well. You know, doing all kinds of things that when you look at a protocol name, whether it comes from Harborview or from University of Washington, it looks the same. And we decided to prioritize the most used protocols as well. So this is a very long project, and it cannot happen just with the physicists. We have to work with the technologists, and we have to work with the radiologists and make it easy on us. So what we did, this is a very busy slide. The point I'm trying to show here is we took those beautiful tables that the techs had made about the codes and indications, and I put in a column saying proposed protocol names. And we wanted to do it so we do it across all our sites, irrespective whether you have a GE scanner, a Philips scanner, or a Siemens scanner. And we said, what can we come up with that will be acceptable to all? Because this will reduce the number of variation for this protocol name in DoseWatch, because that's a real pain for the physicists. So this is our works in progress right now, but it shows you all the names we came up with based on the indication. And we are now working on this project again with the help of our technologists who are very open to working with us in doing this. And I don't know if you see that here in this country, or Sam, you see it at your hospital, or you at your hospital, Tanya. But it's funny, you know, the same protocol will be different from one scanner versus another, the name. And then when it goes down to PACS, it'll be something else. So our goal is, let's have consistent terminology going from the scanner to PACS to the dose monitoring system, so that it makes life easy for all of us. And here's a great resource that Tim, who is a wonderful physicist at University of Wisconsin, and all he does is CT. His whole job is CT. He spends a lot of time on CT. He develops all these wonderful resources that can be used by people like Sam and me, who do many modalities besides CT. And this is basically, he has a wonderful manual on talking about how do you nomenclature for series descriptors, hanging protocols manual, and all kinds of other education for resources. It's open. There's a manual here for dose check, CT education, contrast flow, and so on, that can help you all in many other education for your technologists. So in summary, protocol review and optimization, again, to end this series of lectures, requires all three, radiologists, tech, and physicists. We can't all work without each other. If we are doing all this for the benefit of our patients, we need to work with each other. And the technologist is, in our site anyways, responsible for implementing changes to protocols, updating the protocols online or in a book, if you have it in a book, bringing any issues or problems to the attention of the optimization team, making real scan time decisions. Sometimes they have to make decisions based on what they're scanning, monitoring the dose check alerts, protocoling instead of the radiologist, and interacting with many other professionals to make sure we're doing everything well for our patients. So again, I want to summarize that each of these individuals is important. We cannot do our job. As physicists, I think I speak for Sam and me saying we can't do our job without the help of the radiologist and the technologist. I mean, they're very much essentially an essential part of my job. What I do, I interact with the technologists regularly, and I could not do my job without them. But at the same time, I think physicists bring a unique technical expertise to anything the technologists and radiologists do, and we are here to help. So again, if you start doing protocol review, make sure you're including a professional from each of these professions. Thank you very much.
Thank you so much for the excellent talk and highlight the importance for each other. We are the triplet. We need to get stuck to each other. We cannot separate.
Exactly.
Right.
Exactly.
Right. Yeah. Any questions from the audience? Comments? I would say that I get so spoiled. I get so spoiled not only in the US but also in Thailand in terms of the CT protocol. So in the US, my technologists normally do they know what they have to do in terms of the protocol. They just come to the reading room and ask me for the protocol. If they have some questions or some uncertain, like, the clinician order without and with contrast, I think we just should do just a with contrast only. What do you think? Do you agree or something like that? But majority of the study, because majority of the study, they can protocol themselves by themselves because like we have the indication based. With this indication, this is the protocol that they should do. And also in Thailand, I think majority of the technologists, they know what they have to do. That is in my opinion when I was in Thailand before. Yeah. Any comments? พี่โอมดูเหมือนตั้งท่า
Almost lunchtime. Again, we need to
No questions
emphasis
from
on
him.
the teamwork, and then for whatever we do is for our patient. And I travel a lot for the technologist education. I know that education and training vary a lot from one place to another, and also the medical physicists same way. Radiologists, they are quite harmonized. Like they are doctors are doctors. Radiologists are radiologists. But for radiographers and physicists, it might not be the case. So
one thing I forgot to mention that all our CT technologists have to be certified in doing CT. You cannot take a technologist who does only X-ray and have them put in a CT scanner and do CT. Very important again from a point of view of making sure you have the technical expertise to run a CT scanner as a technologist. You know, if you've been doing X-ray for 10 years and we now throw you into CT, you need to understand the system and all that. So in America, we have the the certification for the technologists. And to do CT by regulations, Joint Commission, I think, requires that. At least my state requires that we should have some training for the technologists that they're trained in CT to run the CT scanner.
I think it's ARRT or something.
Yeah.
So I think right now in Thailand, we are
all in one. We just have one single license, but we are gearing toward the subspecialty.
Quality added certification, something for the CT, ultrasound, and MRI that Dr. Jirapan started at the Jirapan Royal Academy.
Yeah, they're so different, the modalities, that you can't have one person being skilled in all of them.
Yes, and I think like right now, Napapong have done a lot of like a webinar and training for the technologies, and I also like for the IAOC, we are trying to have like an educational course that has like a radiologist teach technologists what they need to look for, like because they are our eyes. They are the first person to see the patient and see the image, and they need to call us, right? So that's why we have those collaboration in terms of training and education. That's great.
We have like free online training for technologists so that they can collect the CPD. The Thai Technology Society does it like twice a month at least. So we have lots of resources.
Right, that's great.
Yeah.
You need to have the same for the physicists.
I think that is the one thing that we can do because like the knowledge that because like our daily practice, we need each other to provide the subspecialty expertise, and that's why we need to have like a more multidisciplinary lectures or something that you show something. This is what I want. Can you provide that things to me? And this is what you want. Can you teach me how I can look for something?
Right.
I think that is the most important thing that we need to like continue the education and like a multidisciplinary lectures or something to share the experience. Okay. Any questions from the audience online from Zoom?
Everyone's hungry.
Everyone hungry, especially Napapong. He want to go for lunch now. So thank you so much everyone for joining us today. I think we're gonna end today on the broadcast session, and in the afternoon we're gonna have some like a review protocol for the internal group person, and then we will come back and see you guys again tomorrow at 8:30. Thank you so much. Bye bye. Thank you. สวัสดีค่ะ